Hello there and welcome to Physics with William, where curiosity settles in, the lights stay low, and science is allowed to move at a human pace. Tonight we're taking up a question that sounds at first like the sort of thing someone might whisper halfway through a late-night conversation after too much coffee and not quite enough sleep. Can you live forever by moving fast enough? It is the kind of question that sits in a strange place between science fiction, real physics, and the very old human habit of wondering whether time can somehow be bargained with, if only we are clever enough. Before we get into any of that, I would love to know where in the world you are listening from and what time it is for you right now. There is something oddly fitting about that, because this whole journey begins with the quiet fact that whatever hour it happens to be in your corner of the world, it is not just a number on a screen or a set of glowing digits on a bedside clock. It is part of the thing we're trying to understand. Time is what carries us from one thought to the next, from one birthday to another, from kettle to teacup, and then somehow to empty mug before we are quite ready for it. And if this little nighttime investigation feels soothing, or interesting, or simply like a pleasant place to let your mind wander for a while, I would be very grateful if you liked the video and maybe subscribed as well. It helps this quiet corner of physics find more people who enjoy a gentler kind of explanation, the sort that does not rush past the strange parts just because they are strange. Now, the question itself sounds almost mischievous. Can you live forever by moving fast enough? Not live a bit longer? Not stay healthy into old age? Not slow down your birthday candles by eating more vegetables and taking brisk walks? We mean something much bigger and much stranger than that. Could motion itself, simple movement through space, change your passage through time so dramatically that you might in some sense outlast everyone else? Could you climb into a ship, travel fast enough, and return to find whole generations gone while only a few years have passed for you? And if that happened, would that count as a kind of immortality? Or would it be something else entirely? Something both more real and more limited than the dream of living forever? At first glance it sounds absurd. Most things do not become immortal by going quickly. A biscuit does not become everlasting because you throw it across the room. A person running late to catch a train is not suddenly granted eternal life by sprinting harder. In everyday life, speed and time seem completely separate. One tells you how fast something moves, the other tells you how long something lasts. One belongs to the car, the train, the planet, the rather determined pigeon crossing the road at exactly the wrong moment. The other belongs to clocks, heartbeats, waiting rooms, and the slightly suspicious amount of time it takes for your toast to pop up when you are hungry. We are used to treating them as different categories entirely. But physics, especially the kind that arrived in the early 20th century and made everyone reconsider what they thought the universe was doing, has a talent for taking things we keep in separate mental drawers and showing that they are deeply connected. Space and time turned out not to be independent after all. Motion and the passage of time were not merely neighbours. They were woven together so tightly that once you started pulling on one thread, the other began to move as well. The strange part is that this is not metaphorical. It is not one of those cases where physicists speak in grand dramatic language, and what they really mean is something mild and technical. When the theory of special relativity says that time slows down for a moving traveller, it means exactly that. Not that the traveller feels busy and therefore the trip seems shorter. Not that their watch is poorly made. Not that they are simply distracted by the in-flight snacks. It means that less time actually passes for them compared with someone who stays behind. That is where tonight takes its turn from curious to unsettling. Because once you say out loud that time can slow down for a moving person, the mind begins to ask the next obvious question. If a little speed slows time a little, then what would a great deal of speed do? If you could move unimaginably fast, fast enough that the ordinary rules of life begin to bend, could you stretch your own experience against the rest of the universe? Could you step into tomorrow while barely aging? Could you keep doing it? Could you continue leaping forward, watching centuries pass outside your own body, while your personal clock ticks along more slowly than everyone else's, it starts to sound less like travel and more like cheating. Human beings have always had a complicated relationship with time. We complain that it goes too slowly when we are bored and too quickly when we are happy. We divide it into years and hours and deadlines as if that helps us control it. We imagine defeating it through memory, legacy, medicine, religion, or pure stubbornness. Some people try to fill time, some try to save it, some try to waste it in peace. But very few of our schemes ever challenge time at the level of physics itself. We usually accept the basic deal. 1 second is 1 second. A year is a year. We all move through life at roughly the same pace, and whatever differences we notice are differences of feeling, not of reality. Special relativity quietly tears up that agreement. It helps perhaps to begin with something familiar. Think of 2 clocks. One sits on a shelf in a quiet room. The other is carried away on a long journey at tremendous speed and then eventually brought back. In ordinary common sense, you would expect the 2 clocks to disagree only if one had been jostled or cheaply made or purchased from a shop with too much confidence and not enough quality control. But in relativity, the disagreement is not a malfunction. It is the point. The travelling clock truly records less elapsed time. It has not merely measured badly, it has lived less time. Already the phrase begins to sound peculiar. Lived less time. We are not used to speaking that way. We think of life as something that unfolds at one steady pace for all of us. But relativity says no. Your motion through the universe changes the rate at which time passes for you. Not enough at everyday speeds to matter in ordinary life, which is fortunate because family gatherings are already complicated without having to ask whether Uncle Martin is 2 microseconds younger than expected after his commute. But at speeds approaching the speed of light, the effect becomes enormous. And that is where our topic starts to sharpen. If enormous speed can reduce your passage through time, then the dream becomes tempting. Suppose you could travel so fast that while decades passed on Earth, only a few years passed for you. You would come back younger than the people who stayed. Not younger in spirit. Not younger in the way people describe a good holiday. Younger in the strict physical sense that fewer years have been written into your body. Your heart would have beaten fewer times. Your cells would have gone through fewer cycles. Your life, as measured from the inside, would have lasted longer relative to the outside world. There is something both thrilling and slightly lonely about that idea. Thrilling because it sounds like a door into the future. Lonely because it means leaving everyone else on the other side of it. Imagine setting off on such a journey while your friends remain on Earth. To you, the voyage might take only a handful of years. You might sleep, eat, read, complain about the ship's coffee, become temporarily obsessed with one very specific maintenance noise, and eventually turn around to come home. But when you arrive, cities may have changed, generations may have passed, and whatever counted as modern when you left might by then be kept in a museum behind glass with a little plaque explaining that people once found it impressive. You would not have outrun death in an absolute sense. You would still age. You would still be mortal. But compared with the world you left behind, you would have crossed a staggering amount of time while spending only a modest amount of your own. That is why people are drawn to phrases like living forever. The idea does not literally promise endless life, but it brushes against something emotionally similar. If you can keep your own experience time small while allowing the universe outside to race ahead, then in a relative sense you can outlast eras. You can witness futures no ordinary lifetime would ever reach. You might not become eternal, but you could become strangely displaced from the usual scale of human existence. There is, however, a catch. There is always a catch. In fact, there are several, and physics is nothing if not diligent about providing them. One cannot simply decide to move fast enough and get on with it. The universe has rules, and among them is the especially firm rule that anything with mass cannot be accelerated all the way to the speed of light. The closer you get, the more difficult the task becomes. Not difficult in the way assembling flat-pack furniture is difficult, where determination and a mildly aggressive screwdriver eventually solve the matter. Difficult in the way climbing a wall that gets taller as you approach it is difficult. The goal keeps retreating into impossibility. Even before that problem, there is the matter of energy. The amount required to push a human-carrying spacecraft anywhere near those extreme speeds is not the sort of thing one finds by cutting back on household heating for a few weeks. We are talking about demands so large that the engineering challenge alone begins to sound like a civilization-wide project, assuming the civilization is having a particularly ambitious century. Then there are practical concerns. The ship must function. The traveller must survive acceleration. Radiation becomes a serious threat. Tiny particles in space, harmless at ordinary speeds, become dangerous at very high ones. Biology, as it turns out, is not especially enthusiastic about being part of a relativistic thought experiment. So no, this is not a hidden route to true immortality. It is not the universe accidentally leaving a loophole open in the back door. You cannot become deathless by driving very quickly. And I say that partly as a matter of physics, and partly in the hope of discouraging anyone from misunderstanding tonight's message in a way that involves the motorway. Still, the fact that true immortality is off the table does not make the real result any less astonishing. Because what special relativity does allow is already far stranger than most fiction dares to be when it wants to sound believable. It allows the possibility that a person can dramatically alter the amount of time they personally experience compared with the amount of time experienced by the rest of the world. That is not fantasy. It is one of the central consequences of modern physics. Perhaps that is why the subject feels so compelling. It touches two different instincts at once. One is scientific curiosity. We want to know how the universe works when common sense reaches its limit. The other is much older and much more human. We want more time, more life, more chances, more mornings, more conversations that do not end because the hour got late, more years for the people we love, more of whatever it is that makes being here feel worthwhile, and when science hints that time itself may be stretchable under the right circumstances, we immediately lean closer. What makes this especially interesting is that the words can mislead us. Live forever sounds like remaining in existence without end. That is not what relativity offers. What it offers is a different relationship between your own lifetime and the wider timeline of the universe. If you travel fast enough, you do not stop your own clock. You slow it relative to others. You do not become infinite. You become delayed. You borrow less of your personal time while the cosmos spends a great deal more of its own. There is a subtle emotional difference there, and it matters. True immortality would mean endless continuation, never reaching the final page. Relativistic time dilation means something more selective and more peculiar. You still turn pages, you just do so more slowly than the world around you. Entire chapters of history could pass while you're only a little older. In that sense, you could make your lifetime reach much farther into the future than it otherwise would. But the number of years you actually feel, the years counted by your heartbeat and memory and body, would still be finite. That may sound disappointing at first. After all, if one begins with forever, anything less can feel like a compromise. But physics has a way of replacing one impossible fantasy with another kind of wonder, because once you really absorb what relativity is saying, the ground shifts beneath ordinary assumptions. Time is not universal in the way we once imagined. The age of a person is not simply a matter of counting calendar pages on Earth. Duration itself becomes partly a matter of path. How you move changes how much time you accumulate. Life is not measured by one single cosmic clock hanging somewhere outside the universe with stern impartiality. There is no such clock. There are only clocks following different journeys and therefore telling different stories. That idea takes some getting used to. It resists intuition because human beings evolved at very low speeds by relativistic standards. We're excellent at throwing balls, missing trains, and estimating how long it takes water to boil when we're impatient, We're not naturally equipped to picture what happens when motion becomes so extreme that time itself begins to separate into different rates for different travellers. Nature did not prepare our instincts for near-light speed. We had to discover that with mathematics, experiments, and the collective willingness of generations of scientists to believe results that sounded completely unreasonable until the evidence insisted. And the evidence did insist, again and again. Not always in dramatic spaceship adventures, sadly, but in careful measurements involving clocks, particles, and technologies that must account for relativistic effects if they are to work properly. The strange slowing of time with motion is not a speculative side note, it is part of how the world actually behaves. So tonight, and over the course of this topic, we're going to take this big unsettling question seriously. Not in the sense of promising a secret recipe for eternal life, because there is no point pretending physics says what it does not say, but in the much more interesting sense of asking exactly what motion does to time, how extreme that effect can become, what sort of future a fast traveller could reach, and why all of this comes so close to the dream of living forever without ever fully becoming it. For now, it is enough to notice that the doorway opens with a single quiet fact. Move faster, and time for you slows relative to those who remain still. Everything else follows from that. The possibility of jumping into the future, the image of a traveller returning younger than those who stayed behind, the seduction of calling this immortality, the sober correction that it is not, the practical obstacles that turn a theoretical possibility into an almost unthinkable engineering challenge. All of it begins here, with motion and clocks, and a universe far stranger than everyday life lets on. And once that first fact settles in, the next step is unavoidable. We need to understand why motion changes the clock at all, because that is where the real story starts to gather speed. It is one thing to hear that moving fast can slow down your time, and quite another to understand why the universe would behave in such an inconveniently dramatic way in the first place. After all, most of us grow up with a very simple picture of time. It is there in the background, steady and reliable, minding its own business while everything else happens inside it. Cars move, planets move, people move, toast burns, trains leave without us. But time itself seems like the one part of reality that ought to stay put and keep ticking at the same rate for everyone. That picture feels natural because it works well for almost everything we do. If you walk across a room, you do not notice your watch behaving oddly. If you ride a bicycle down a quiet street, you do not arrive home mysteriously younger than your neighbour who stayed in the garden. Everyday life gives us no obvious warning that time and motion are linked. On ordinary human scales, the effect is far too small to notice. So we build our instincts around a world where time seems universal, and for most practical purposes that is good enough. But physics has a habit of becoming less intuitive the more carefully you look. What feels obvious is often only approximately true, and sometimes the approximation is so comfortable that we mistake it for reality itself. That is what happened with time. For centuries, people assumed that if two events happened at the same time for one observer, then they happened at the same time for everyone. It seemed perfectly reasonable. If a church bell rings in one town while a lantern is lit in another, then either those things were simultaneous or they were not. What else could there be to say about it? The answer, rather annoyingly, is quite a lot. To understand why motion changes the clock, we have to start not with clocks at all, but with light. Light turns out to be the troublemaker in this story, the detail that refuses to fit comfortably inside the old picture of space and time. In older ways of thinking, motion worked the way common sense says it should. If you are standing still and someone rolls a ball toward you, the ball has a certain speed. If you start walking toward it, the ball reaches you faster. If you walk away, it reaches you more slowly. Speeds add and subtract in the obvious way. This is so familiar that we barely think about it. The same logic seems like it ought to apply to light. If a beam of light is moving toward you and you move toward it, common sense says you should measure it coming at you faster. If you move away from it, you should measure it coming at you more slowly. That is what a Newtonian universe would lead you to expect. Motion would simply stack on top of motion, neat and tidy, like adding extra speed to a rolling suitcase that was already moving down an airport floor because someone forgot to zip it properly. But nature does not do that. The speed of light stays the same, not approximately the same, not the same only when it is convenient, the same for all observers, regardless of how they themselves are moving. This is the key fact, the one that forces everything else to change. Once the speed of light is fixed for everyone, something else has to give. Space cannot remain what we thought it was. Time cannot remain what we thought it was. Simultaneity cannot remain what we thought it was. The whole framework has to be rebuilt. It is hard to overstate how strange that is. Imagine you're on a train moving very quickly and you shine a flashlight toward the front of the carriage. In ordinary intuition, someone standing on the platform would say the light is moving at the speed of the flashlight beam plus the speed of the train. But they do not. They still measure the light moving at the same speed that you do on the train. The only way for that to be true is if the measurements of distance and time themselves adjust, depending on the motion of the observer. This is where relativity stops being a theory about objects and starts becoming a theory about measurement itself. It says that reality does not come with one single universal set of distances and times that all observers must agree on. Instead, different observers moving relative to each other can each make perfectly valid measurements, and those measurements can differ, not because one of them is mistaken, but because space and time are not absolute background stages. They are part of what motion reshapes. A useful way to get a feel for this is to imagine a very simple clock, the kind physicists like, because it behaves more politely than real clocks with springs and gears and batteries that somehow only fail when you most need them. Picture a clock made from two mirrors facing each other, one above the other, with a pulse of light bouncing between them. The light goes up, hits the top mirror, comes down, hits the bottom mirror, and repeats. Each round trip marks a tick. It is a very clean clock because its ticking is based on light itself. Now imagine you're sitting beside this clock on a spaceship moving smoothly through space. To you, the light simply travels straight up and straight down between the mirrors, a steady rhythm. Tick, tick, tick. Nothing dramatic. The clock is doing its job, but now consider someone watching that same spaceship fly past from the outside. To that observer, the light inside the moving clock does not go straight up and down. Because the ship is moving sideways while the light travels, the light follows a diagonal path. As it goes upward toward the top mirror, the whole apparatus has moved along, so the light has to cross a longer slanted route to meet the mirror. Then the same thing happens on the way down. From the outside, the light is tracing a zigzag path, not a simple vertical one. Here comes the crucial point. The speed of light is the same for both observers. The person on the ship and the person outside both agree on that. So if the outside observer sees the light travelling along a path and the speed is unchanged, then the journey must take more time. That means the moving clock ticks more slowly from the outside point of view. Nothing has gone wrong with the clock. It is not broken. It is not lazy. It has not become emotionally distant. It is working exactly as it should. The reason it ticks more slowly is that the geometry of motion plus the fixed speed of light leaves no other option. Once you accept that light keeps the same speed for everyone, slower ticking for the moving clock is not a weird extra consequence you bolt on later. It is built into the structure of the situation, and if that light clock slows, then so must every other process that belongs to the moving traveller. A real person is not made of mirrors and a bouncing pulse of light, but the logic reaches much farther than that one toy example. All physical processes are embedded in a universe where light plays a fundamental role. Chemical reactions, nerve signals, the operation of atoms, the entire machinery of a living body, all of it unfolds within the same relativistic structure. So when we say the moving clock runs slowly, we are not making a narrow claim about one clever device. We are saying that time itself passes differently along that moving path. This is the part that can feel slippery at first, because language encourages a misleading picture. It is tempting to imagine that there must be some deeper correct time hiding underneath, and that one observer merely sees an illusion because of the motion. But relativity is not about appearances in that shallow sense. It is not like looking at a distant tower through heat haze and seeing it shimmer. The slower ticking is real within the relationship between those two observers. The disagreement is not a failure of perception, it is a feature of reality. Even more unsettling, the effect goes both ways. If you are on the spaceship, you can regard yourself as at rest and the outside world is moving. From your perspective, it is their clocks that seem slow. This is where many people first suspect the whole thing has finally become too ridiculous to continue. Surely both sides cannot be slower than the other. That sounds less like physics and more like a committee meeting, where everyone insists someone else has the missing paperwork. But this is where the relativity of simultaneity enters, the deeper shift that makes the rest consistent. Observers moving relative to one another do not slice the universe into shared moments of now in the same way. They do not agree on which distant events are happening at the same time. That may sound like an abstract technicality, but it is actually central. Once simultaneity becomes relative, the apparent symmetry in time slowing is no longer a contradiction. It is part of a new geometry of space and time in which different observers lay down different coordinate grids on reality. This is worth sitting with, because it is not merely a detail in the machinery. It is the reason motion changes the clock at all. Time does not slow for moving objects because the universe likes drama, or because high speed somehow gums up the gears of watches. Time slows because the old assumption of a universal shared temporal order turns out to be false. The rate at which time accumulates depends on the path taken through space and time together. Motion changes that path and therefore changes the amount of time experienced. An everyday analogy can help, provided we do not push it too far. Imagine two people taking different routes across a landscape. One walks straight over a hill, another winds around it along a flatter road. Both begin and end at nearby places, but the distances they cover are not the same because the terrain gives structure to the journey. In relativity, time is somewhat like that, except the landscape is not ordinary ground and the routes are not merely spatial. Different motions trace different histories through the combined fabric of space and time, and those histories do not all contain the same amount of experienced time. That is why the question is never simply how long the trip took according to someone else. The real question is how much time passed for the traveller themselves. In ordinary life, we assume those answers will match closely enough to ignore the distinction. At relativistic speeds, they do not. The traveller and the person who stayed behind may reunite having lived different amounts of time. That possibility does not emerge from some quirk of biology. It comes directly from the way motion reshapes temporal experience. At this stage, people often ask whether the clock is really slowing, or whether it only looks that way because of the signal delay from light reaching the observer. That is a good question, and physics takes it seriously. If a distant ship moves away from you, the signals it sends do arrive more slowly. That is a separate effect, a communication delay. But relativity is not merely about delayed appearances. When observers account properly for signal travel and compare clocks carefully, the time dilation remains. It is not just that you see the moving clock differently, it is that the clock genuinely records less elapsed time between meetings. This has been tested in several ways. High-speed particles created in the upper atmosphere survive longer than they would if time passed for them at the same rate it passes for us on the ground. Their internal processes are slowed relative to Earth. Precise clocks flown around the world do not come back matching identical clocks that stayed put. Modern navigation systems must account for relativistic effects, because clocks in motion do not keep the same time as clocks at rest relative to the Earth. The universe is not being metaphorical about this. It means it. There is also something important to say about what motion cannot do. It does not make the traveller feel strange in the moment, at least not if the motion is smooth and steady. If you are inside a spacecraft moving at a constant speed, There is no special sensation telling you that your time has slowed relative to somebody else. Your heartbeat feels normal. Your thoughts feel normal. Your breakfast is still disappointingly finite. Locally, everything proceeds as usual. That is one reason the effect is so hard to internalize. From the traveller's own point of view, nothing about their personal flow of time seems altered. It is only in comparison with someone following a different path that the difference becomes apparent. This is an essential point because it protects relativity from turning into mysticism. Time dilation is not about feeling dreamy or entering a trance or somehow floating outside ordinary life. It is exact, physical, and comparative. Each observer experiences their own time normally. The difference appears when their histories are set side by side. There is a stern kind of elegance in that. The universe does not privilege your viewpoint with special labels saying this is the true time, and those are the distorted versions. Instead, it gives each observer a legitimate account of events shaped by their motion, and then asks us to be disciplined enough to accept that reality is richer than our habits of thought. If that sounds demanding, it is because it is. Human intuition was not trained on spaceships near the speed of light. We learned our lessons in villages, fields, roads, and living rooms, where all speeds were tiny compared with the ones that make relativistic effects obvious. So our instincts say that time is separate from motion. Physics says the instincts are useful but limited. The deeper truth is that motion alters the structure within which time is measured. There is also a nice irony here. We often talk as though clocks measure time the way rulers measure length, as if they were passive tools that merely report what is already there in a universal form. But relativity reveals that clocks are not measuring some single cosmic flow that every observer taps into equally. A clock measures the time along its own journey. It records the duration of its path through the universe. Change the path, and you change the reading. In that sense, clocks do not simply sit beside reality taking notes. They participate in the geometry of reality itself. This is why motion changes the clock. Not because velocity is magical, not because time is a substance that gets tired when you move quickly, and not because Einstein wanted to make exams more difficult for future students, although one could be forgiven for suspecting him of exactly that. Motion changes the clock because the speed of light is fixed, because simultaneity is not universal, and because time is woven together with space in such a way that different motions lead to different amounts of elapsed time. Once that is understood, even in a rough and intuitive way, the big question about living forever starts to look more precise. The issue is no longer whether speed somehow grants immortality by a mysterious trick. The real issue is whether by moving fast enough, a traveller can reduce their own passage of time so dramatically that they cross vast stretches of the future while using up only a small portion of their life. The answer begins here, with the simple but world-changing fact that the clock on the move does not keep pace with the clock at rest. And once Einstein took that fact seriously, he did something extraordinary. He stopped treating it as a curious side effect and built an entirely new way of thinking about time from it, which is where the story becomes even stranger. For a very long time, people assumed time was the most dependable thing in the universe. Space might be messy, matter might move unpredictably, weather might ignore your plans with a kind of cheerful disrespect. Human beings might promise to arrive at 6 and mean something closer to past if traffic, mood, and dinner all interfere at once. But time surely was meant to be steady. It was supposed to flow evenly for everyone, everywhere, whether you were sitting quietly under a tree or racing across the sea or staring at the ceiling at 3 a.m, wondering why the brain chooses that exact hour to remember something embarrassing from 8 years ago. That older picture was not foolish. It worked beautifully for ordinary life and for a great deal of science. Isaac Newton built an enormously successful framework on the assumption that time was absolute, which means that it passed the same way for all observers no matter how they moved. In that view, the universe had one great shared clock behind the scenes. Everything happened inside that common rhythm. Different people might disagree about where things were, because position depends on motion and perspective. but not about when things happened in any deep sense. Time was the stage manager, impartial and invisible, calling the cues for the whole cosmos. Then Einstein came along and said, in effect, that this reassuring picture could not survive the behavior of light. There is something almost mischievous about that. You can build a whole worldview around solid things like apples, planets, cannons, trains, and then the thing that overturns it all is a beam of light refusing to behave the way common sense expects. That was the trouble. Experiments and theory were both pointing toward a deeply strange fact. The speed of light in empty space was always the same, regardless of how the observer moved. Not usually the same. Not the same after a bit of adjustment. The same. This was not a mild inconvenience for old physics. It was a crisis. Einstein took that crisis more seriously than anyone else. In 1905, he published the theory we now call special relativity. It did not begin with a dramatic machine or a brand new particle or a cosmic explosion. It began with a rule. A very strange rule, but a rule all the same. The laws of physics should be the same for all observers moving at constant speed relative to one another, and the speed of light should also be the same for all of them. Once he accepted those two ideas fully, everything else followed with a kind of relentless logic. Time could no longer remain universal. It had to bend. This is where the subject shifts from merely clever to deeply unsettling, because Einstein was not proposing that clocks malfunction when they travel fast. He was saying something much more radical. The very amount of time that passes depends on motion. If two observers move differently, they do not necessarily age by the same amount between the same pair of meetings. There is no master cosmic clock hiding behind the curtain to tell us who got it right. Each observer has their own time, and motion changes it. That is Einstein's strange rule for moving time. The faster you move relative to someone else, the more slowly your time passes relative to theirs. It is a compact sentence, but it takes a moment to appreciate how much of ordinary intuition it overturns. We're used to thinking of speed as changing where you are, not how quickly you become older. If you run for a bus, you may arrive sooner, or breathless, or both. But you do not expect the bus stop to have aged a different amount than you. Yet special relativity says that, in principle, motion does alter your aging. At ordinary speeds, the effect is tiny, laughably tiny, so tiny that everyday life can ignore it and still get along perfectly well. But the effect is real, and at very high speeds it becomes enormous. What gave Einstein the confidence to say something so outrageous was that the alternative was worse. If the speed of light is fixed for everyone, then the old assumptions about space and time cannot both survive. You cannot keep universal time and keep the constant speed of light as well. One of them has to go. Einstein chose to keep the speed of light and rebuild time around it. That decision sounds almost philosophical, but it was not guesswork or personal taste. It was driven by the evidence and by the demand for consistency. If you imagine different observers moving relative to one another, and each measuring the same beam of light, the numbers only fit together if distances and times transform in a new way. The world must adjust its bookkeeping. The cost of preserving light's constant speed is that clocks no longer agree universally. This becomes easier to grasp if we revisit the kind of imaginary light clock we considered earlier, the one where a pulse of light bounces between two mirrors. That clock is useful because it strips away mechanical distractions. No gears, no springs, no batteries, no little red light blinking at you in a passive-aggressive way. Just light moving between mirrors. If you're travelling with the clock, the light goes straight up and down. But if someone watches you from the outside while you move past, they see the light tracing a longer slanted path. Since both of you must agree on the speed of light, the outside observer has no choice but to conclude that the moving clock ticks more slowly. Einstein understood that this was not just a cute trick with an artificial device. If one clock built from light must tick more slowly when it moves, then every process that can function as a clock must slow in the same way. A heartbeat is a kind of clock. A chemical reaction is a kind of clock. The oscillation of atoms is a kind of clock. Biological aging itself is a clock. Motion affects all of them because they are all physical processes unfolding in the same universe. So the rule is not about watches, it is about duration itself. There is also something important and subtle about the word relative here. When we say your time passes more slowly relative to someone else, that is not the same as saying you feel anything odd in the moment. From your own point of view, your life continues normally. You think thoughts at the usual pace. You get hungry at the usual pace. Your tea still cools in the mildly disappointing way tea always does when you become distracted. Nothing about your private experience announces that you have entered a relativistic state. The difference only appears when your history is compared with someone else's history. This is where Einstein's rule begins to feel less like a trick and more like a redefinition of reality. Time is not a universal flow through which all beings drift together. It is a personal measure attached to the path you take. In relativity, the passage of time belongs to the traveller. Each observer carries their own temporal account, and motion changes how much time is withdrawn from it. That may sound abstract, but it has a very concrete implication. If two people begin together, then separate so that one undergoes very fast motion, while the other remains behind, and then reunite, they may find that different amounts of time have passed for them. One has genuinely aged less. That is not a psychological impression. It is not due to fatigue, boredom, or an exciting playlist. It is written into the clocks, the bodies, and the structure of space-time itself. At this point, one naturally asks why the universe should be built this way. Why should light be the thing that forces time to change? Why should motion steal duration from the traveller rather than simply altering position? There is no deeper why in the sense of a moral reason or a purpose. Physics is not in the business of telling us why reality chose its rules, as though the universe had a committee meeting and voted after refreshments. What physics does tell us is that once those rules are in place, especially the fixed speed of light, this is how space and time must behave if the world is to remain consistent. And consistency mattered deeply to Einstein. One of the remarkable things about his work is that he trusted logical structure more than familiar intuition. He was willing to say that if intuition and physical law disagree, it is intuition that must be retrained. That takes a certain kind of courage because common sense has social support. It feels safe. If everyone believes time is universal, then saying otherwise sounds almost rude, like correcting grammar at a wedding. But Einstein followed the consequences all the way through. One of the most surprising consequences is that simultaneity breaks apart. Before relativity, it seemed natural to ask whether two distant events happened at the same time. After relativity, the question no longer has a single universal answer. It depends on the observer's motion. Two lightning strikes that seem simultaneous to one observer may not be simultaneous to another moving relative to the first. This sounds like a side issue, but it is really central. If observers do not agree on what counts as happening now at distant places, then they cannot all share one universal time. The very idea of one giant synchronized cosmic present begins to dissolve. That is part of what makes Einstein's rule so strange. It does not merely adjust clocks, it dismantles the notion that the universe comes packaged into one agreed sequence of moments for everyone. There is no single universal now stretching across the cosmos, like a giant invisible shelf on which all events sit together. Different observers moving differently slice reality into past, present, and future in different ways. For human beings, this is emotionally inconvenient. We like the present. We like imagining that there is one shared now we all inhabit together, that somewhere the universe has a master page labelled current moment, and we're all on it. Relativity suggests the universe is under no obligation to provide such comfort. Time is more local than that, more personal, and more entangled with motion than common sense ever suspected. Still, Einstein's rule is not chaos. It is not saying that anything goes, or that clocks become arbitrary once you move. Quite the opposite. The whole beauty of relativity is that it replaces an older, simpler order with a deeper and more precise one. The rules are exact. Once you know the relative motion between observers, you can determine how their measurements of time and space relate. The strange part is not that the universe has lost structure, it is that the structure is richer than we guessed. This richness also means that moving time is not some optional effect that appears only in imaginative scenarios. It is present all the time, though usually in tiny amounts. Particles moving near the speed of light in laboratories live longer than they would if time passed for them at ordinary rates. Precise clocks carried on aircraft or satellites do not stay synchronized with identical clocks left on Earth unless relativity is taken into account. Systems like global navigation depend on corrections from both special and general relativity to remain accurate. The world keeps confirming Einstein's strange rule, quietly but firmly. Perhaps that is the most astonishing part. The theory feels like it ought to belong to a very narrow corner of physics, some distant place occupied by fast spaceships and patient mathematicians. Yet its consequences reach into technology, astronomy, and the practical running of modern life. The universe does not care whether we find the rule intuitive. It applies it anyway. There is also an important limit built into this story, and Einstein's rule hints at it even before we discuss it directly. The effect of time slowing becomes more dramatic as speed increases, especially as one approaches the speed of light. But the very structure of special relativity makes the speed of light a boundary for anything with mass. You can get closer and closer, and the time effects can become more and more extreme, but you cannot simply go all the way and become a beam of light yourself. The universe has drawn a hard line there. That matters because it clarifies what moving time can and cannot do. Motion can reduce the amount of time you experience relative to others. It can let you leap forward into the future in a very real sense. It can make your life, measured against the calendar of the wider world, stretch farther than it otherwise could. But it does not let you stop your own time completely. It does not let you freeze aging outright. Einstein's rule is powerful, but it is not magic. It changes the rate, not the fact, of mortality. Even so, the emotional pull of the idea is easy to understand. If you can move fast enough that only a few years pass for you while decades pass for Earth, then from one perspective you have effectively travelled into the future. You have not lived forever, but you have crossed a great deal of history while spending only a modest amount of your own life. That is already enough to make the mind race ahead. What if the trip were longer? What if the speed were greater? What if you kept doing it? How far into the future could a person go while remaining only middle-aged by their own clock? Those questions are all children of Einstein's strange rule. Without it, the dream vanishes. With it, the dream becomes physically meaningful, even if brutally difficult in practice. Special relativity does not offer immortality, but it does offer something that once would have sounded equally impossible. It allows different people to accumulate different amounts of time simply because they moved differently. There is a kind of humility in that. Human beings used to imagine the universe arranged around our intuitive categories. Space here, time there, motion happening inside both, all of it neat and manageable. Einstein showed that the deep structure is more subtle. The world is not organized to match our first impressions. It is organized according to principles that remain true whether or not they feel comfortable inside the skull of a primate trying to drink tea and understand infinity at the same time. And yet, once the initial strangeness settles, there is also something beautiful about the rule. It ties light, motion, and time into one coherent picture. It says that the passage of time is not a separate background melody playing behind the universe, but part of the same composition as movement through space. To move differently is to live differently in time, not metaphorically, literally. This is why Einstein's contribution was not just a correction to Newton, but a transformation in our understanding of reality. Newton's universe had one clock for all. Einstein's universe gives each traveller their own. Newton's time flowed the same for everyone. Einstein's time depends on motion. Newton's now was universal. Einstein's now is local and relative. Each step feels small when stated plainly, but together they amount to a completely different conception of existence. If that sounds like a lot to place on the shoulders of one rule, it is. But the universe seems content to be built that way, and physics has spent more than a century checking the details and finding them stubbornly correct. The faster you move, the slower your time passes relative to someone else. That is Einstein's strange rule for moving time. It is simple to state, difficult to absorb, and impossible to ignore once you see where it leads. Because once time itself can slow, the next question becomes unavoidable. How much can it slow? Not a tiny laboratory effect, not a delicate correction for satellites, but a dramatic human scale difference. If someone could travel fast enough, what would happen to their aging, their body, and their place in history compared with the people who stayed behind? That is when the idea stops being merely strange and starts becoming personal. By now the central idea has started to settle in, even if it still feels a little unnatural when held too closely. Motion changes time. Not your mood about time, not your estimate of time, not the vague human feeling that a good evening vanishes too quickly, while a dull meeting stretches into geological history. We are talking about actual elapsed time, the kind that gets written into clocks, cells, and the steady unfolding of a life. And once that fact is in place, the next step is both simple and deeply unsettling. If motion slows your time, then the faster you go, the less you age compared with the people who remain behind. That sentence sounds almost too dramatic to belong to real physics. It has the shape of science fiction. It sounds like something a film trailer would say in a very serious voice, while showing a lonely spaceship and at least one person looking out of a window with the expression that means they are about to lose everyone they know to the future. But the physics underneath it is not invented for effect. It follows directly from special relativity. If you move fast enough relative to someone else, your clock runs more slowly relative to theirs. And since your body is not separate from time, but one of the many things living inside it, you age more slowly too. It is worth pausing on the word age, because it can make the idea sound more mystical than it really is. Aging is not some separate curse sitting outside biology, sprinkling oldness on us at fixed intervals. Aging is the sum of physical processes. Cells divide, molecules react, structures wear down, repair systems work and then gradually work less well. Hormones shift, tissues change, memory accumulates, and so does damage. All of that unfolds in time, so if less time passes for you, then less aging happens to you. Not because you have discovered an elixir, not because your body has become unusually virtuous, simply because your personal timeline contains fewer elapsed years. This is one of the most extraordinary consequences of relativity, because it turns age into something less universal than people once imagined. We usually talk about age as though it were obvious and shared. If two babies are born on the same day, then after 10 years they are 10 years old. After 50 years they are 50. Simple enough. But relativity quietly inserts a condition we do not usually notice. That remains true only if their journeys through space-time are sufficiently similar. Separate them. Send one on a voyage at extraordinary speed. Bring them back together. Now age is no longer just a matter of birthday count on a common calendar. It becomes a matter of path. That idea can feel almost rude to common sense. Common sense wants fairness. It wants symmetry. If two people start together and then meet again later, surely they ought to have aged the same amount unless one had an unusually stressful time of it. But physics is not organised around what feels socially reasonable. It is organised around the structure of reality, and reality says that different motions can lead to different amounts of elapsed time. If one person spends a long period moving at speeds close to the speed of light, they can return having lived fewer years than the person who stayed behind. There is something eerie about that because we normally treat aging as the most personal and unavoidable of all processes. You cannot outsource it. You cannot argue with it. You cannot ask it to wait politely while you finish a project. And yet relativity shows that aging is not entirely sealed inside the body. It depends on how the body moves through the universe. That does not make aging optional. It makes it relational. A useful way to think about this is to remember that your body contains many clocks, even if you never call them that. Your heart keeps one kind of time, your neurons keep another, your metabolism keeps another. The decay and renewal of molecules inside you is a kind of timekeeping. Sleep cycles, hormone rhythms, cellular repair, all of these mark duration in one way or another. When relativity tells us that the moving traveller's clock runs slowly, it is telling us that all these processes unfold more slowly relative to the outside observer. The traveller remains perfectly normal to themselves. They do not feel suspended. Their thoughts do not stretch out like slow syrup. Their lunch does not take 4 weeks from the inside. But when they are compared with someone who stayed behind, fewer biological events have occurred in their body. That is what it means to say they aged less. Imagine, for example, a traveller who boards a ship capable of reaching an enormous fraction of the speed of light. To the people on Earth, the ship races away at a speed so high that relativistic effects become significant. They watch years pass in the usual way. Seasons turn. News cycles come and go. Governments change. Buildings are constructed and renovated and occasionally demolished in a fit of progress. Children grow up. Dogs become old and dignified or old and unreasonable depending on temperament. All the ordinary churn of life continues, but on the ship fewer years pass. The traveller still experiences time in a normal human way, yet the total amount of time they accumulate is smaller. So if the Earth experiences 20 years while the traveller experiences 5, then upon reunion the traveller is 5 years older and everyone back home is 20 years older. That is not a metaphor. It is a literal age difference produced by motion. The traveller has not merely preserved a youthful outlook. They have, in the strict physical sense, undergone less aging. This is often where the mind begins to race ahead of the details. If speed slows aging, then why not go faster still? If very high speed means fewer years for the traveller, then perhaps sufficiently extreme speed means almost no aging at all compared with the outside world. At that point, the thought starts to resemble a loophole in mortality. Perhaps you cannot stop time, but perhaps you can ration it. Perhaps you can spend so little of your own that the universe outside grows ancient while you remain relatively young. That intuition is not entirely wrong. In principle, as your speed approaches the speed of light, the time dilation becomes more and more dramatic. You do not have to remember equations to grasp the basic point. The closer you get to that cosmic speed limit, the more fiercely time seems to resist passing for you relative to the people you left behind. A journey that might correspond to many decades outside could consume only a few years for the traveller. Push the speed closer still, and the contrast grows even sharper. Whole stretches of history could slide by while the traveller lives through a comparatively modest span of personal time. This is why relativity is often described as a kind of one-way time travel. It does not let you go backward. It does not let you revisit your childhood, or prevent yourself from making that haircut decision you were talked into at 19. But it does let you move into the future faster than everyone around you, in the sense that you can arrive at a later era while aging less than the people who remained in the ordinary flow of earthbound life. And because aging is so central to how we understand mortality, that future travelling effect naturally becomes entangled with the dream of living longer. After all, if you can make your own 5 years line up against somebody else's 20, then in one sense you have stretched your life. Not stretched it from the inside, because 5 years still feels like 5 years to you, but stretched it against the world. Your finite lifetime can be made to reach farther into the future than it otherwise could. There is something both thrilling and melancholy in that thought. Thrilling because it hints that human life need not be chained to one historical era. Melancholy because the price of reaching the future this way is letting the present go without you. The traveller does not get extra time with the people they leave behind. They get less. They trade shared years for future years. That is the emotional truth hiding inside the physics. To age slowly relative to Earth is not simply to win more life. It is also to lose synchrony with everyone who stayed. That makes the effect feel less like a cheat and more like a bargain. Physics does not hand you immortality wrapped neatly in the gift paper of velocity. It offers something stranger. You may keep more of your own biological youth, but only by allowing the rest of the universe to move on ahead. There is no free extension of life within the same human world. There is only a widening gap between your clock and theirs. Still, the sheer fact that this is possible at all remains astonishing. It means that age is not an absolute quantity written into the universe by a single external bookkeeper. Age depends on world line, though one need not use the formal word to appreciate the idea. It depends on the route you take through space-time. Different routes can contain different amounts of personal time. You might begin beside someone, separate, and later return younger than they are despite having been born on the same day. That possibility alone is enough to make the old common sense picture feel suddenly flimsy. One reason this can be hard to absorb is that we instinctively imagine ourselves watching a fast traveller from outside like seeing a car rush past. From that viewpoint, it feels natural to say that their clock slows and their aging slows, but relativity is more subtle than that. The traveller, from their own perspective, is not experiencing an obviously strange internal life. They wake up, think, move and age normally according to their own sense of time. They do not feel themselves becoming preserved. Their body does not whisper congratulations for entering a less aging-friendly frame of reference. What changes is the comparison between them and those who follow a different path. This matters because it prevents the whole subject from becoming mystical or vague. Relativistic slowing of aging is not like folklore about enchanted sleep or hidden valleys where no time passes. It is precise and comparative. Each person lives their own time locally. Different amounts of time are accumulated only when those local histories are contrasted. That is why actual reunion is so important in these stories. The difference in aging becomes concrete when two people who shared a starting point meet again after one has moved very differently. The famous example, of course, is the twin story. One twin stays on Earth, the other travels at very high speed and returns younger. We will come properly to that scenario later, because it deserves careful handling and is often told in ways that make it sound more paradoxical than it really is. But even before getting into its details, it gives a human shape to the general rule. The faster traveller ages less, not because youth has become their personal talent, but because fast motion reduced the amount of time they experienced. There is also an important practical lesson tucked inside this. At everyday speeds, the effect exists but is tiny beyond ordinary concern. Your morning commute does not make you meaningfully younger than someone who stayed home. Even air travel, though measurable with highly precise clocks, produces absurdly small differences in human aging. One is not going to return from a holiday and find that everyone else has aged dramatically, while one remains mysteriously fresh-faced and demanding attention. Relativity is real at those speeds, but not dramatically so. To get truly significant slowing of aging, one must approach speeds far beyond anything we can achieve with current human spaceflight. That is one reason the idea remains so tantalizing. The principle is settled physics. The practical realization is another matter entirely. Nature allows the effect but asks for an almost outrageous entrance fee in energy and engineering. The universe is willing to let your aging slow, but only if you are prepared to move with extraordinary speed. Even then, one must be careful with the language of forever. The faster you go, the slower you age relative to others. Yes, but slower is not the same as stopped. However dramatic the time dilation becomes, your own clock still moves forward. Your heart still beats, your thoughts still unfold, you still live minute by minute from the inside. So the phrase live forever can be misleading if it suggests endless subjective existence. Relativity does not give you an infinite personal lifespan. It gives you the power, in principle, to make your finite lifespan correspond to a much larger span of external history. That is no small thing. Suppose a traveller could spend 10 years of personal time on a journey while centuries pass on Earth. They would not be immortal, they would still be 10 years older. But they would have crossed centuries. Their life would have reached into a future unavailable to someone who remained still. In that sense, they would have extended their experienced lifetime relative to the rest of the universe. The body ages, history races. The traveller stands between the two, finite in one direction and far-reaching in the other. The more one thinks about it, the more this begins to feel like a very particular answer to a very ancient desire. People have always wanted more time, but there are at least two different things we mean by that. One is more time from the inside, more conscious years of living, more mornings, more ordinary days. The other is more reach into the timeline of the world, more chance to see what comes next. Relativity helps mostly with the second. It does not give you unlimited internal years. It lets your limited years carry you farther into the future outside yourself. That distinction matters because it keeps the science honest. A fast traveller is not escaping their own mortality. They're rearranging its relationship to history. Instead of dying in roughly the same era in which they were born, they may die in a much later one, having personally lived fewer years than the outside calendar might suggest. They are still mortal, but they become historically displaced. There is something almost haunting about that image. A person leaves one century and arrives in another, while preserving more of their youth than anyone who stayed behind. They have, in a real sense, outrun their contemporaries, yet they have not defeated time. They have only experienced less of it. In ordinary life, we think of surviving into the future as requiring us to keep going while the years accumulate. Relativity reveals another route. Let the years accumulate elsewhere while you carry fewer of them yourself. Perhaps that is why the idea remains so captivating. It is not the fantasy of endless life in the crude sense. It is subtler and more plausible, and therefore, in some ways, more disturbing. True immortality would place you outside the usual human condition entirely. Relativistic slowing of aging keeps you inside it, while stretching your relation to the world beyond recognition. You remain a person with a finite lifespan, but that lifespan can be set against the timeline of civilization in a radically different way. And none of this is a matter of interpretation or philosophy. The effect has been confirmed in the behaviour of fast-moving particles, in the operation of precise clocks, and in technologies that would fail if Einstein had been mistaken. The faster you go, the slower you age relative to those at rest with respect to you. The statement sounds almost literary, but physics means it literally. So the question is no longer whether motion changes age. It does. The deeper question is what such a journey would actually amount to for a human being. What would it mean to leave Earth, move fast enough to age slowly, and come back to a world that had moved on without you? What kind of future could you reach? How far ahead could you leap? And would arriving there feel like triumph, loss, or some uneasy mixture of both? That is where the story begins to shift from principle to experience, because once we know that speed slows aging, the next thing to imagine is the voyage itself. Once you accept that high speed can slow aging, the next image arrives almost on its own. A ship, a traveller, Earth falling away behind them. Not because the idea is merely dramatic, though it certainly is that, but because a spaceship is the clearest way to imagine what special relativity actually allows. If time passes more slowly for someone moving fast enough, then a person aboard a sufficiently fast ship could leave home, spend only a limited number of years in transit, and return to find that many more years had passed on Earth. That is not fantasy in the loose sense. It is the natural consequence of the rule we have been following. Motion changes the clock. Fast enough motion changes it by a lot. And once it changes by a lot, a spaceship becomes something more than a vehicle. It becomes a machine for travelling into the future. That phrase deserves a little care, because time travel has a way of encouraging the wrong kind of excitement. People hear it and immediately imagine paradoxes, vanished ancestors, impossible warnings sent backward across history, and at least one person trying to prevent a haircut or an awkward conversation. This is not that sort of time travel. A relativistic journey does not let you visit the past. It does not let you rewrite anything. It does not let you step outside cause and effect and start rearranging events like furniture. What it allows is something both simpler and more believable. You go forward, but you go forward unevenly compared with the people who stayed behind. Your personal years and Earth's years separate. If the difference becomes large enough, then from the point of view of ordinary human life, you have jumped ahead. Imagine it in the most concrete way possible. You leave Earth at the age of 30. You board a ship capable of travelling at a speed so high that relativistic effects are no longer tiny but overwhelming. You spend 5 years on the journey according to your own clocks. You sleep in your cabin. You argue politely with the onboard computer about a maintenance alert that turns out to be both real and unhelpfully vague. You exercise because the body, unlike the imagination, does not become stronger merely by being placed near deep scientific ideas. You eat, read, think, and watch the stars shift in ways no one on the ground ever sees with the naked eye. To you, time feels normal. 5 years is 5 years. It does not feel compressed or stolen or enchanted. It feels like living. Then you return. But Earth has not shared your pace. Perhaps 50 years have passed there. Perhaps 100, depending on the details of the journey. Cities have changed. Languages have drifted in little ways. Technology that seemed advanced when you left is now a museum piece, described by future school children with the same respectful disbelief we reserve for room-sized computers and telephones attached to walls. The people you loved are old or gone. Places are familiar only in outline, and standing there in the middle of all that change, you're not a person who has lived for 50 years. You're a person who has lived for 5. You have not merely observed the future, you have physically arrived in it while spending less of your life than the calendar on Earth has spent. That is what riding a spaceship into the future means. It is useful to dwell on the ordinariness of the traveller's own experience, because this is where relativity often becomes most unsettling. The ship is not a magical coffin in which time pauses. The traveller is not frozen. They are alive all the while. Their body continues. Their mind continues. They still wait for meals, still get tired, still have days that feel productive and days that feel strangely flat for no obvious reason. The future is not reached by skipping existence. It is reached by allowing your personal time to proceed more slowly relative to another place. That is why the concept feels so real once it settles in. It does not ask you to believe in suspended animation, only in the actual behaviour of time under extreme motion. This leads to a very peculiar truth. You do not need to live for a century to see a century from now. You need only to follow a path through space-time that lets fewer years accumulate in you than in the outside world. That may sound like a technical distinction, but it changes the emotional meaning of the journey completely. The traveller is not made immortal. The traveller is made temporally displaced. They belong biologically to one span of years and historically to another. Their body says one thing, the calendar around them says another. People sometimes describe this as cheating time, and one can see why. There is a mild sense of unfairness to it, almost as though the traveller has found a queue that moves faster than everyone else's, except in this case the queue is history itself. While others must endure each intervening year one by one, the relativistic traveller lets the outside world do most of the waiting. Earth bears the burden of the decades. The traveller pays only a handful of years from their own life to cross a much larger span of civilization. And yet it does not feel like cheating for long, because the cost becomes obvious the moment you imagine the human side of it. Suppose you leave behind friends, siblings, parents, perhaps a partner, perhaps children. Suppose the trip will take only a few years for you, but many decades for them. You are not borrowing free time from nowhere. You are giving up shared time. That is the exchange. You preserve more of your youth, but you lose the ordinary continuity of life with the people who remain behind. They do not accompany you into the future. They age through it in the usual way while you arrive late to the era you have chosen. There is something quietly brutal about that. The future is won by surrendering the present. That is why this kind of time travel feels so different from fantasy. In fiction, the future is often visited like a destination. One presses a button, steps through a portal, opens a hatch, and there it is. Relativistic travel is harsher. It demands that the journey itself still be lived. You do not leap instantly from one century to another. You work your way there through your own limited years while the outside world accumulates far more. The future is not free, it is purchased with separation. Still, the scientific idea remains irresistible because it tells us that the future is not sealed behind an absolute wall. It can be reached in a way that is physically meaningful. A person in a fast enough ship can arrive at a much later Earth while remaining comparatively young. That possibility alone would have sounded absurd to most of human history. For thousands of years, the future was something one entered only by aging in step with everyone else. Now, physics says there is another route. You can take fewer of your own years with you than the world spends in the meantime. It also helps explain why a spaceship is such a natural vehicle for this thought experiment. Space is where prolonged extreme speed makes sense. On Earth, even our fastest machines are nowhere near the kind of velocities that would produce dramatic human-scale time dilation. A fast aircraft can produce tiny measurable effects. A satellite can require relativistic corrections. But if you want to imagine someone visibly outpacing the aging of those left behind, you need something far more extreme. You need a craft built not for tourism or orbit, but for a sustained near-light speed journey. The emptiness of space provides the room for that idea. It is not that space itself causes the time shift. It is the speed. But space gives the speed somewhere to happen. Once you place a human being inside such a vessel, the ordinary and the extraordinary begin to mix in interesting ways. The traveller might spend months watching instrument panels, reviewing trajectory adjustments, exercising to preserve muscle and bone, sleeping in carefully timed cycles, listening to recorded voices from a world that is aging faster than they are. Messages from Earth would become peculiar things. If communication were possible, the traveller might receive words from people who, on the ship's timeline, seem almost unchanged from yesterday, while on Earth entire stretches of life have passed since those words were first sent. Letters would become fossils in transit. By the time they arrived, the sender might be much older or no longer alive. The emotional difficulty of the trip would not come only from isolation, it would come from desynchronization. And when the traveller finally turned homeward, the return would not restore the lost symmetry. That is one of the saddest and most fascinating parts of the idea. Going back to Earth is not going back to your own time. Earth will have moved on. The home you return to may be the same planet, but it is not the same moment in history that you left. The ship can carry you through space and into the future, but it cannot preserve the ordinary timing of your place in the world. This makes the journey both more meaningful and less triumphant than people first imagine. To ride a spaceship into the future is not to defeat time, but to choose a different relationship with it. You can stretch your reach into history, yes. You can see eras that would normally lie beyond your lifespan. You can, in principle, witness the long unfolding of civilization while spending relatively little of your own life. But the deeper implication is that history becomes something you pass through unevenly. You stop being synchronized with your century. You become a person carried forward by an unusual clock. That may sound lonely, but it is also a remarkable expansion of what it means to be human in the universe. Before relativity, a lifetime was tied very tightly to one historical band. You were born, lived, and died within a certain range of years, and however long you lasted, you remained broadly within the same era as your peers. Relativistic travel breaks that expectation. It says a person's biological lifespan and their historical reach can come apart. You may live only a few decades by your own clock, and still witness portions of the far future that no ordinary stationary life could touch. There are obvious reasons why this appeals to the imagination. People want to know what comes next. They want to see whether humanity thrives or fails, whether cities become cleaner or more absurd, whether medicine gets wiser, whether we finally stop making devices that need urgent updates the moment they're removed from the box. A relativistic ship offers, at least in theory, a way to witness outcomes that would otherwise remain hidden behind the simple limitation of lifespan. It is a scientific route to futurism, not prediction, but visitation. And yet even here one must keep the physics honest. The traveller is not moving into a future that has been paused waiting for them. They are being carried into it while the universe around them proceeds normally. That means the future they arrive in is not guaranteed to be pleasant, legible, or survivable in cultural terms. A person who jumps a century ahead may find not wonder, but estrangement. Technology may be advanced, but so may social norms, language, law, and the quiet expectations that allow daily life to make sense. The traveller may have outrun aging relative to Earth, but not dislocation. In fact, the very success of the journey guarantees a form of dislocation. There is also a subtle philosophical point hiding in all this. When people ask whether a spaceship can take you into the future, they often assume the future is a place you either can or cannot reach. But we are all reaching it all the time. The real question is, how much of your own time must you spend to get there? In ordinary life, the answer is 1 year of your life for 1 year of Earth's future, more or less. Relativity changes that exchange rate. It lets a traveller spend fewer personal years to reach more Earth years. That is what makes the ship a future machine, not because it creates the future, but because it changes the cost of arriving there. Seen that way, the ship becomes almost like a device for temporal leverage. A modest amount of subjective time can move you across a much greater amount of external time. That is an extraordinary power, but it remains bounded by the fact that your subjective time is still finite. You do not stop paying altogether, you merely pay less than everyone else. The universe is offering a discount, not a waiver. If all this sounds emotionally mixed, that is because it is. There is genuine wonder in the idea of a human being stepping out of a ship into an era far beyond their birth. There is also grief in knowing what that implies for everyone they left behind. The traveller becomes both explorer and exile. They gain history at the cost of belonging. They carry youth into a world where all the familiar reference points may be gone. That tension is part of what makes relativistic future travel so compelling. It is scientifically plausible and emotionally expensive, which is often a sign that an idea has touched something real. And the closer we look, the clearer it becomes that this is not merely an entertaining consequence at the edge of relativity. It is one of the clearest examples of what the theory means in human terms. The faster you go, the more your time separates from the time of those who do not go with you. At some point, that separation is no longer a tiny correction. It becomes a story, a life, a difference in age, memory, and historical location large enough to feel almost mythic. That is why the spaceship matters. It gives the principle a human frame. Without the traveller, time dilation can remain a clever fact about clocks and particles. With the traveller, it becomes personal. It becomes the possibility of leaving one world and arriving in another without having lived through all the years in between. It becomes the strange situation in which someone can return younger than their own contemporaries. And once that picture settles in, another question appears almost immediately. If motion can make one person age less than another, then what happens when the comparison is not just between traveller and society, but between two people who began together, shared the same age, and then parted ways? That is when the idea stops feeling merely futuristic and starts becoming intimate. There is a reason the twin story has become the most famous way of explaining relativistic time. It takes an idea that already feels strange in the abstract and pins it to something human and impossible to ignore. Two people, same birth date, same childhood, same number of candles on the cake every year. Then one of them leaves on a very fast journey and comes back younger than the other. Not younger in the flattering sense. Not younger because they took fewer responsibilities or used a more determined moisturizer. Younger in the plain physical meaning that less time has passed for them. Fewer years have been written into their body. Fewer years have been lived. That is a powerful image because it presses directly on our instincts about fairness, identity, and time. We can tolerate the idea that clocks disagree if the clocks are machines. Machines are always doing irritating things. We can even tolerate the idea that particles behave oddly at very high speed because particles have never been particularly interested in helping us feel comfortable. But when the story becomes two human beings who begin side by side and later reunite with different ages, the strangeness becomes personal. It is no longer just a lesson in theoretical physics. It feels like a challenge to the ordinary meaning of growing older. So let us imagine them carefully. Two twins are born on the same day. They grow up together. At some point in adulthood, one remains on Earth while the other boards a spacecraft capable of extraordinary speed. The travelling twin leaves, spends time moving at a speed close to the speed of light, turns around and eventually returns home. When the journey's over, the twin who stayed on Earth has aged more. The twin who travelled is younger. That, in broad outline, is the famous scenario. At first, this sounds like a contradiction waiting to happen. After all, special relativity says motion is relative. From the point of view of the twin on the ship, one might say that Earth is the thing moving away and then moving back. So why should the ship twin come home younger rather than the Earth twin? If each observer can regard the other as the one in motion, then should not each see the other as aging more slowly? This is why people often call it a paradox. It seems as though symmetry should protect equality, yet the result is unequal aging. The good news is that the physics is not actually contradictory. The bad news, if one enjoys a calm evening of uncomplicated intuition, is that the resolution reveals just how differently time works from what common sense expects. The key point is that the two twins do not live equivalent histories. The twin on Earth remains in one inertial frame for the whole story, speaking loosely, while the travelling twin does not. The travelling twin leaves, changes direction and comes back. That change matters. The trip is not one long uniform motion extending forever. It includes departure, turnaround, and return. Those stages make the two paths through space-time genuinely different. And once the paths are different, the total amount of time accumulated along them can be different too. This is where people sometimes become suspicious, as though acceleration were being smuggled in as a technical excuse after the fact. But acceleration is not the reason time dilation exists. High speed itself already changes the rate at which time passes. The importance of the turnaround is that it breaks the symmetry between the twins. One twin can remain in the same broad temporal relationship to Earth throughout. The other cannot. To come home younger, the traveller must leave and later rejoin the stay-at-home twin, and that means changing frames along the way. It helps to strip the story back to its simplest emotional core. The twins meet at the start. They meet again at the end. Between those meetings, they follow different routes through space-time. One route includes a fast outward leg and a fast return leg. The other is the ordinary route of remaining on Earth. When the twins compare clocks at reunion, the route with the high-speed travel contains less elapsed personal time. The traveller is younger because their path through the universe simply includes fewer years. That way of putting it may sound almost too neat, but it gets to the heart of the matter. In relativity, elapsed time is not just a matter of counting the same universal flow from different seats. It depends on the path taken. The twins begin together and end together, but the histories between those meetings are not interchangeable. One path uses up more time than the other. There is a useful analogy here, though like all analogies it should be handled gently. In ordinary space, two travellers can begin at the same place and end at the same place while covering different distances if they take different routes. One might take the direct road, another might wander through side streets, hills, and scenic detours for reasons that seemed persuasive at the time. No contradiction arises from the fact that they covered different distances. They followed different paths. Relativistic time works in a somewhat similar way, except what differs is not just distance in space, but duration experienced along a path through space-time. The twins reunite having travelled through reality in different ways, and those ways do not contain equal amounts of personal time. What makes the story so compelling is that the difference is not hidden inside a machine, it shows up in people. One twin has lived more birthdays, one has more grey hair, one may remember cultural changes, the other skipped almost entirely. The reunion is not only a physical fact, but a social and emotional shock. Imagine the traveller stepping out of the ship still feeling close in age to the sibling they left behind, only to meet someone noticeably older. The difference is not a matter of attitude, it is written into faces, bodies, memory, and history. This is also the moment when the idea of riding into the future becomes intimate rather than merely grand. With a spaceship and a civilization, one can talk loosely about leaping ahead. With twins, the loss becomes measurable in family terms. Shared time has been broken. The travelling twin did not simply preserve youth against the abstract background of Earth. They lost years with a specific person. The one who stayed behind had to live all those extra years in the ordinary way, one day after another, while the traveller accumulated fewer of them. That is an important emotional correction to the fantasy of relativistic travel. It is easy to focus on the apparent benefit. The traveller is younger. The traveller has aged less. The traveller has reached farther into the future while spending fewer years. All true. But the twin story makes clear what this costs. You do not get extra shared life with the people you love. You get less shared life. You keep more youth, but at the price of desynchronizing yourself from those who remained in the old flow of time. The physics is beautiful, but it is not generous in the sentimental sense. There is also another subtle lesson in the twin scenario. It teaches that time is not just what clocks display when left undisturbed in matching rooms. Time is bound up with history, motion, and reunion. If the twins never met again, one could talk forever about what each one said the other's clock was doing during the voyage. But the power of the story lies in the fact that they do meet again. The disagreement is no longer a matter of perspective at a distance. It becomes a direct comparison. One clock, one body, one life has undergone less elapsed time than the other. Because the subject can feel slippery, people often ask at what point the younger outcome is decided. Is it during the high-speed cruising? Is it during the acceleration? Is it at the turnaround? The most honest answer is that the full result belongs to the whole journey. The long periods of high speed are what generate most of the difference in elapsed time. The turnaround matters because it changes the traveller's frame and allows the comparison at reunion to come out asymmetrically. Without that switch, there is no neat coming home to compare ages, but it is not as though the ship twin suddenly becomes younger in a single, magical instant during the turn. The age difference builds from the overall structure of the trip. A practical way to picture this is to imagine the twins carrying perfect clocks. At departure, they synchronize them. The traveller heads out, later reverses course and returns. When they finally stand together again and look at their clocks, the traveller's has advanced less. Since the body is itself a kind of biological clock, the traveller's body has advanced less too. The result is physical, exact, and unavoidable. No amount of arguing at the reunion changes the reading. This is one of those points where relativity reveals its seriousness. It does not care that the outcome sounds unfair. It does not smooth things over for the sake of emotional symmetry. The twins are not granted equal aging just because they started equal. Equality at the beginning does not guarantee equality at the end when the histories in between differ. Nature is not sentimental about such things. Still, one should not let the harshness of the result hide its elegance. The twin story is not a bizarre loophole or a failure of the theory. It is one of the clearest demonstrations that the theory hangs together. Once you understand that time is path-dependent, and that the traveller and the stay-at-home twin do not follow the same kind of path, the younger return is not only possible, it is required. And because it is required, the story becomes a powerful way of thinking about what motion really does to a human lifetime. Before relativity, one might have said that travel changes where you are, and perhaps what you see, but not how much life you have used up. After relativity, that statement is no longer safe. Travel at extraordinary speed changes the amount of life spent between departure and reunion. The twin who goes out and comes back does not merely visit distant places, they alter the rate at which their lifetime is consumed relative to the sibling who stays. That gives the whole subject a distinctly human weight. We are not just discussing clocks in laboratories or particles in accelerators. We are discussing the possibility that two people with the same starting age can part and reunite with different biological ages because one moved differently through space-time. There is a reason this continues to fascinate people long after they have forgotten the finer details of the theory. It touches something very deep in how we imagine a life. We think age belongs only to the body and the calendar. Relativity says age also belongs to the journey. There is another interesting aspect to the twin story, and it concerns the meaning of home. In ordinary life, home is where time is supposed to feel stable. It is the reference point from which journeys depart and to which they return. But in relativity, home does not anchor universal time. It only anchors one particular path. The Earth twin's life is not more correct. It is simply one route, one history, one accumulation of years. The ship twin's life is not distorted. It is another route, another history, another accumulation. When they reunite, the Earth twin has more elapsed time not because Earth owns the true clock of the universe, but because that route through space-time contains more time between the same meetings. That is one of the most mature things relativity asks us to accept. There is no hidden referee holding up a card marked real time. There are only actual histories and the durations they contain. This is difficult for intuition because our language is full of terms like same moment and same age and same now, all of which suggest a universal background order. Relativity keeps most of the everyday language but quietly removes the old certainty underneath it. And once you absorb that, the twin story changes from a puzzle into a window. It shows how a human life might be stretched against history without being stretched from the inside. The traveller still lives each day normally. What changes is how many outside years those days correspond to. The younger twin has not escaped life. They have crossed it differently. Of course, at this stage, another question begins to stir. If one twin can come home younger after a sufficiently fast journey, then one might be tempted to ask whether this is not in effect a form of immortality. If you could keep leaving and returning, always aging slowly compared with those who remain behind, could you continue carrying your younger body farther and farther into the future? Could repeated relativistic journeys make you functionally eternal in comparison with ordinary human history? It is exactly the kind of question the twin story invites, because the outcome already feels like a small rebellion against time. But the story also contains the seeds of the answer. The traveller is younger, yes, but not ageless. The ship twin still aged, their clock still advanced, their body still changed. They simply used up fewer years than the Earth twin during the shared interval between meetings. The difference is dramatic, but it is not absolute. Relativity lets you save time relative to someone else. It does not let you stop spending it altogether. That distinction matters more than it first appears. It is the line between deep extension and true forever. The twin who comes home younger has not defeated mortality. They have only changed its rate relative to another person's timeline. Yet that rate change can be so large that it almost tempts us to speak in the language of immortality anyway. Almost, but not quite. And that is where the next part of the journey begins, because once the younger twin has stepped off the ship and proven that motion can carry a person past the aging pace of everyone left behind, the natural temptation is to ask whether this trick could be pushed all the way to forever, or whether something essential still stands in the way. By the time the travelling twin comes home younger, it becomes very hard not to ask the next question. If moving fast can make you age less than everyone else, then could that begin to feel like a kind of forever? Not forever in the strict mathematical sense, because physics is not a fairy tale and does not usually hand out infinite lifespans as a reward for clever travel plans. But perhaps forever in the human sense, long enough to outrun generations, long enough to watch centuries pass while only a modest number of years collect in your own body. Long enough that ordinary people would look at your life and say that whatever you are doing is close enough to immortality to make the distinction feel rude. It is a tempting thought, and one can see why it holds on so tightly. If a person could leave Earth, travel fast enough for time on board to slow dramatically, then return to find that decades or centuries had passed here, while only a few years had passed for them, that person would seem to have done something astonishing with time. They would not merely have lived a normal life in an unusual place. They would have altered the relationship between their own lifespan and the rest of history. Their body might have aged 10 years while civilization aged 100. To anyone watching from the outside, that starts to look very much like escaping the ordinary human deal. But the phrase from the outside matters a great deal, because this is exactly where the subject becomes more subtle than the fantasy first suggests. There are really two different questions hiding inside the one about living forever. One is how your life looks compared with the timeline of the wider world. The other is how your life feels from the inside while you're actually living it. Those are not the same question, and relativity answers them differently. From the outside, the case can seem almost overwhelming. Suppose you take repeated relativistic journeys. Each one consumes only a handful of your personal years, while much larger spans of time pass on Earth. Over the course of what feels to you like a few decades of lived life, you might carry yourself across centuries of planetary history. New governments, new languages, new technologies, new cities, perhaps even new understandings of what it means to be human could come and go while you continue forward in a body that is aging much more slowly than the world around it. In historical terms, you would begin to seem almost impossible, not literally indestructible, not unkillable, not endless, but strangely detached from the ordinary pace at which human lives vanish into the past. Seen that way, time dilation can indeed imitate certain aspects of immortality. It can make one person endure across many eras. It can let a finite life reach far deeper into the future than it otherwise could. It can turn a human being into a witness to long stretches of history without demanding that they endure all those years in the ordinary biological way. If immortality means remaining present while the world changes around you, then relativity can produce something uncannily similar. But from the inside, matters are very different. The traveller still wakes up every day. The traveller still feels hunger, fatigue, boredom, curiosity, loneliness, and the occasional irrational confidence that this time the maintenance panel really is making a new sound. They still live through 1 hour and then another. They still accumulate memories in sequence. Their body still moves through its own limited stock of days. Nothing about relativistic motion turns those days into an endless ocean. A year still feels like a year. 10 years still feels like 10 years. Your own time does not become infinite just because Earth is spending much more of its time in the meantime. This is the central point, and it is easy to miss if one becomes too enchanted by the big calendar difference. Time dilation changes the exchange rate between your personal time and the outside world. It does not give you an unlimited balance. You're still spending life. You're simply spending it in a way that purchases more future. That is a useful way to think about it, because it explains both the power and the limitation at once. Imagine your life not as a fixed number of Earth years, but as a reserve of experienced time. Every day you live uses a day from that reserve. Relativity cannot stop the spending. You do not get to stand outside your own becoming, but if you travel fast enough, each day spent from your reserve can correspond to many days, years, or even more in the outside universe. So your finite personal duration can be stretched across a much larger historical distance. That is extraordinary. It is also not forever. Would it feel like forever? Probably not. In fact, it would almost certainly feel very ordinary in the immediate sense. Your breakfast would still occur one morning at a time. You would still get restless on long journeys. You would still count the passing of your own days in all the usual ways. The deepest trick of relativity is that it produces dramatic differences in comparison without necessarily producing dramatic sensations in the moment. The traveller does not feel themselves becoming immortal. The traveller simply lives at their own normal pace while history outside them runs ahead. There is something almost disappointing in that if one hoped for a grand internal experience. We imagine immortality as a huge emotional state, some great feeling of endlessness or release from the clock. Relativistic time dilation offers nothing so theatrical. It does not flood your mind with eternity. It gives you normal Tuesdays that happen to be carrying you farther into the future than normal Tuesdays have any right to, and yet that very ordinariness may be what makes it so powerful. Because if you think about it long enough, the realization becomes quietly unsettling. A person might live through what feels to them like a standard adult lifespan, and still emerge into a world centuries beyond the one they were born into. They would remain subjectively finite while becoming historically elongated. That is not how we usually imagine the shape of a life. We think a lifespan and an era belong tightly together. Relativity loosens that bond. There is also a psychological question hiding here. Even if time dilation does not feel like forever in the strict internal sense, might it still produce some emotional imitation of immortality because of the way you relate to everyone else? Suppose you can repeatedly leap ahead. Suppose every time society begins to feel familiar, you leave again, travel fast, and come back to a later world while preserving more of your youth than anyone who stayed. After several such journeys, you might have watched not one generation but many pass away. Your own life would no longer be anchored to the usual social rhythm of birth, adulthood, aging, and death among peers. The pattern would keep breaking around you. In that sense, you might begin to feel less like an ordinary participant in history and more like an observer drifting from age to age. That could feel like a kind of practical immortality, at least for a while. Not because you no longer age, but because everyone around you seems to age and disappear much faster. The same way a mountain can appear eternal next to the brief lives of insects, even though the mountain too will eventually wear away, a relativistic traveller could appear almost timeless against the short continuity of unassisted human history. People would be born into a world where your story already existed, grow old while you remained relatively unchanged, and die before you had added many more years to yourself. If that is not immortality, it is certainly close enough to make dinner conversation uncomfortable. But this is where the emotional cost begins to come sharply into focus. One of the hidden comforts of ordinary mortality is that we mostly age together. Friends grow older with us. Siblings, classmates, partners, colleagues all move through life at broadly the same pace. We lose people, yes, and sometimes cruelly early. But the structure of ordinary time still gives us the expectation of shared development. Childhood belongs to one phase, adulthood to another, old age to another. Relativistic travel disrupts that companionship. If your personal years are repeatedly slowed relative to others, then the world becomes full of people who are synchronized with one another but not with you. You preserve your youth by surrendering your membership in a common age. Would that feel like forever? Or would it feel like dislocation? The answer may depend on what people actually mean when they dream of immortality. Often what they say is that they want endless life, but what they really want is not to lose what they love. They want more time with particular people, more chances to learn, build, enjoy, repair, wander, and remain present in a world that still feels inhabited by the familiar. Relativistic time dilation is poor at granting that wish. It can carry you into the future, but not keep your companions beside you unless they go too. If they stay behind, your preserved years are purchased at the cost of their absence. In that sense, the experience could feel less like immortality, and more like controlled bereavement repeated across history. That sounds severe, but it is built into the logic of the thing. If you age slowly compared with Earth, then Earth is moving on without you. The people there are not being preserved in sympathy. Their clocks keep their ordinary pace. So every relativistic leap is also a separation event. You are not only arriving in the future, you are abandoning shared time in the present. That may be worth it for exploration, for knowledge, perhaps for survival under special circumstances, but it is not a gentle path to eternity. There is another reason time dilation would probably not feel like forever from the inside, and that reason is memory. Human life is not measured only by duration, but by the continuity of remembered experience. A life feels long partly because of how much it contains. If you live 20 subjective years and use those 20 years to cross 200 calendar years outside, your memory still contains only about 20 years of lived material. You may arrive in a distant future, but your inner narrative is not vast in proportion to the historical distance crossed. You have not experienced those outside centuries, you have bypassed them. That is a crucial difference. A truly immortal being in the ordinary fantasy sense would carry the accumulated burden and richness of all the centuries personally lived. They would remember one age after another because they had been present through each of them. A relativistic traveller does something different. They let centuries pass elsewhere while personally living only a fraction of them. So even if their biography spans a huge external range, their internal biography remains limited by the years they actually experienced. In that respect, time dilation feels less like endless life and more like selective skipping. One can make the point more simply. There is a difference between watching every season of a very long series and fast-forwarding through most of it. At the end, you may have reached the same late episode, but you did not live through the same amount of story. Relativistic travel is rather like that. It can carry you to the late episodes of history, but you do not internally become a being of endless duration. You remain a finite creature who has skipped ahead. This matters because the fantasy of forever usually includes not just survival, but accumulation. People imagine becoming old in knowledge, but not in frailty, deep in memory, but not exhausted by it. They imagine a great extended selfhood. Relativity does not supply that kind of endless accumulation. It gives you reach, not infinity. It gives you historical extension, not boundless personal duration. Still, reach is not trivial. A person who can witness centuries within a modest subjective lifespan is inhabiting a profoundly unusual relationship to time. They may see social changes so large that ordinary generational memory cannot hold them together. They may become an outsider to their own origin period. They may experience a peculiar form of loneliness that no stationary person ever quite knows. The loneliness of surviving into times that were never meant for you while scarcely aging by comparison. That could feel in some moments like power and in others like exile. There is also the question of meaning. Ordinary human life derives some of its shape from the fact that time is scarce and moves at about the same rate for everyone around us. We plan around shared calendars. We commit to people because our futures are intertwined at roughly the same speed. We think in terms of growing up with others, building with others, retiring with others. If your own time can be slowed dramatically relative to everyone else, then the social meaning of long-term plans changes. Relationships become harder to anchor. Institutions become more temporary from your point of view. Culture itself may begin to feel thinner because each return reveals that much of what once seemed stable was actually quite brief. A person repeatedly moving through time in this way might begin to feel not immortal, but detached. And yet perhaps some would welcome exactly that. Not everyone dreams of immortality because they long for continuity. Some dream of it because they long to see more, to know what happens next, to observe the long arc of science, politics, language, architecture, medicine, perhaps even life beyond Earth. For such a person, time dilation might feel less like a painful dislocation and more like a hard-won privilege. They would accept the limited subjective years because those years are buying access to futures no ordinary lifespan could touch. To them, it might not matter that forever from the inside remains impossible. Historical reach may be enough. In that sense, whether time dilation feels like living forever may depend on which part of forever matters most to you. If forever means endless subjective existence, then no. Relativity does not provide it. Your own days continue one by one. Your body continues to age according to the time you personally live. If forever means remaining present across many eras of the outside world, then yes, or at least almost yes. You can become a person whose life is scattered across centuries, a living bridge between epochs, a biological finite being with a historically stretched presence. The distinction may sound technical, but emotionally it is huge. One kind of forever is about inner continuity without end. The other is about outer longevity relative to the world. Relativistic travel offers only the second. It lets your life cast a longer shadow across history than your subjective years alone would suggest. That is remarkable, but it is not the same as endlessness. There is also a final humility in the matter. Even if one could ride near light speed over and over, one would still remain vulnerable to the ordinary conditions of life. Accidents, disease, radiation, mechanical failures, simple biological limits, all would remain relevant. You would not become invincible. You would become hard to place on a normal timeline. That is not nothing, but it is not the overthrow of mortality people usually imagine when they say forever. The universe permits a stretching of perspective, not a cancellation of finitude. Perhaps that is the deepest lesson. Time dilation comes very close to one of humanity's oldest dreams without ever fully granting it. It says you may preserve more of your own years than others do while crossing larger spans of history. You may arrive in futures that would otherwise be unreachable. You may seem almost immortal when compared with ordinary lives. But inside your own skin, life remains a sequence of finite days. You still wake, you still wait, you still age, you still move forward through your own limited store of time, so the experience would likely feel less like being eternal and more like being unsynchronized. Less like becoming deathless and more like becoming difficult to date. Less like stepping outside time and more like negotiating a peculiar contract with it, one in which you accept fewer shared years in exchange for greater historical range. That is a strange bargain, perhaps a magnificent one, but still a bargain. And once that becomes clear, another question naturally follows. If time dilation can only imitate immortality from certain angles, then what prevents it from going further? Why can we not simply push the speed high enough to make our own time nearly stop altogether? What is the actual physical barrier that keeps this idea from turning into true forever? That is where the romance of the thought experiment runs directly into the rules of the universe. By the time we arrive here, the temptation is almost irresistible. If moving fast slows your time and moving very fast slows it dramatically, then surely the obvious answer is to keep going faster. Faster and faster still. Push the ship harder. Chase the effect all the way to its limit. If a great speed lets you age less than everyone else, then perhaps the greatest possible speed would let you age almost not at all. And since light itself already seems to inhabit a strange place in relativity, always moving at the same speed for every observer, one might wonder whether the final step is simply to join it. Become fast enough, and perhaps time would finally surrender. This is exactly where physics places a firm hand on the door and says no. Not no in the vague everyday sense, where no sometimes means perhaps later, or with better funding, or after someone important signs a document. No in the deeper sense that the structure of the universe does not permit it. Anything with mass cannot reach the speed of light. That statement is so familiar that it risks sounding like a slogan rather than a profound physical boundary. But it is one of the central rules of modern physics. It does not merely say that getting to light speed is very difficult, or that our present technology is inadequate, or that future engineers will need an especially determined set of spreadsheets. It says that for a massive object, light speed is not a destination waiting at the end of better propulsion. It is a limit built into the geometry of reality. To see why, it helps to remember what special relativity did to our picture of time. The closer a massive traveller moves to the speed of light, the more slowly time passes for that traveller relative to someone at rest with respect to the point of departure. That much we already know. So one might think of speed as a kind of dial. Turn it up a little and time slows a little. Turn it up a lot and time slows a lot. Then perhaps one could simply keep turning until the traveller's time nearly stops. But the dial is deceptive, because the closer you get to the cosmic limit, the harder it becomes to gain each additional bit of speed. Nature does not let you approach light speed in a neat linear fashion. It becomes more stubborn the closer you get. At everyday speeds, our old Newtonian instincts work reasonably well. Push something harder and it goes faster. Give it more energy and it gains more speed in roughly the way common sense expects. A bicycle, a football, a train, a rather ambitious shopping trolley on a windy day all behave in ways that fit the ordinary idea that velocity can keep increasing if one keeps providing enough effort. Special relativity does not ruin that picture immediately. It waits patiently until the speeds become enormous. Then it reveals that the ordinary rule was only ever an approximation. The deep issue is not that objects suddenly become heavy in the naive sense, as though a fast ship somehow fills with invisible bricks the moment it becomes interesting. The better way to think about it is that the relationship between added energy and added speed changes drastically as you approach light speed. More and more of what you pour into the motion goes into a relativistic struggle that yields less and less increase in velocity. The ship keeps accepting energy, but the reward in terms of additional speed becomes increasingly miserly. You can get closer and closer, but you can never actually arrive. This is one of those places where the universe behaves less like a road and more like an asymptote, though there is no need to use the formal term aloud to appreciate the idea. Imagine walking toward a horizon that always remains ahead of you. Every step brings you nearer, genuinely nearer, yet the horizon itself is never reached because it is not a normal location on the ground. Light speed is like that for things with mass. You may approach it without end, but you do not cross into it by effort alone. There is no final triumphant moment where the ship clicks over from almost light speed to exactly light speed, and everyone on board applauds while the instruments make a tasteful sound. Another way to see the problem is to ask what would happen if a massive object actually could reach the speed of light. Special relativity would then drive time dilation toward an extreme in which the traveller's own passage of time relative to the outside would collapse in a way that no longer fits the behaviour of matter as we know it. The theory separates the behaviour of light from the behaviour of massive objects very sharply. Light does not have mass. It does not need to be accelerated up to its speed. It simply exists with that speed as part of its nature. Matter is different. Matter lives on the slower side of that boundary and can never be promoted into the status of light by enthusiasm, ambition, or even a civilization-wide engineering effort. This distinction matters because it keeps us from imagining light speed as if it were merely the fastest lane on an otherwise ordinary motorway. It is not that. It is more like a different category of existence within the theory. Light lives there naturally. Mass does not. A beam of light is not a heavy thing that happens to be moving very quickly. It is a massless phenomenon whose very identity is tied to that speed. Asking a spacecraft with mass to reach light speed is therefore not like asking a slower thing to become faster in the usual way. It is asking matter to behave like something it is not. That may sound abstract, so let us make it more concrete. Suppose you have a ship and you keep accelerating it. At first, everything looks normal enough in concept. More fuel, more thrust, more speed. But as the speed climbs into a truly relativistic range, each further increase becomes harder to achieve than the last. You are not pushing against a simple resistance like air drag or mechanical friction. You are pushing against the structure of space-time as it governs massive bodies. The amount of energy required to keep shaving away the remaining gap grows without bound. Not large, not absurd, unbounded. The closer you demand to get, the more wildly the cost rises. This is why physicists speak of the impossibility not merely as an engineering difficulty but as a principle. If the amount of energy required becomes effectively infinite at the limit, then the limit is not one you conquer by patience. You do not reach it in the way a climber reaches a mountain summit after enough food and determination. There is no amount of practical improvement that turns infinite demand into a manageable project. That is what makes the light speed barrier so severe. It is not a current technical challenge waiting for a future breakthrough. It is woven into the rulebook. Once you absorb that, several things become clear at once. First, time dilation can be made dramatic but not absolute for massive travellers. Your time can slow relative to the outside world by extraordinary amounts, enough to make your finite life reach far into the future, but it never truly stops. Second, the dream of living forever by simply going faster runs into a hard boundary. However impressive your ship, however efficient your propulsion, however heroic your travel posters, you remain on the mortal side of the divide. Third, light itself remains a special case. It is not a model for what humans can become through motion. It is a reminder of the boundary humans cannot cross. There is also an emotional lesson hidden here. Much of the appeal of relativistic travel comes from the thought that perhaps one can buy more future with less personal aging. Physics says yes to a point, but human imagination is rarely satisfied with a point. Once given an extraordinary effect, it immediately asks for the maximum version. If slowing time is possible, why not stop it? If reaching the future is possible, why not leap arbitrarily far? If aging less is possible, why not avoid aging altogether? The light speed limit is where the universe answers those escalating desires with something stern and clean. You may have a great deal, but not everything. You may stretch mortality relative to history, but not abolish mortality itself. One could say that special relativity is generous up to the edge of severity. It permits astonishing amounts of temporal distortion. It allows a traveller to outpace the aging of those left behind. It allows journeys in which centuries might pass outside, while only decades or less pass within. But it refuses to let a being with mass step fully into the domain where its own time would cease in the relevant sense. It grants reach into the future without allowing escape from finitude. This brings us back to the role of mass itself. Mass is not just extra luggage carried by matter. It is part of what locates matter on one side of the relativistic divide. Because a massive object cannot naturally move at light speed, it must always remain in a regime where its own proper time, the time experienced along its path, continues to advance. Slowed relative to others, perhaps dramatically so, but advancing nonetheless. That is why a spaceship traveller can come home younger than people on Earth without ever becoming frozen in time. Mass keeps the story human. It prevents the traveller from crossing into something unrecognisable. There is also a practical intuition worth building here. In everyday life, we're used to limits that are soft. You may not be able to run a mile in a certain time today, but with enough training you might improve. An aircraft may have a speed ceiling, but new materials and engines can push that ceiling higher. We are trained by technology to see limits as invitations. Whenever a sign says impossible, modern culture tends to squint at it and assumes someone will eventually ignore it successfully. That instinct has served humanity well often enough that it is understandable. But the light speed limit is not that kind of sign. It is not erected by ignorance or material weakness. It comes from the form of the laws themselves. This does not mean science becomes dull at the boundary. On the contrary, the boundary is part of what gives the theory its shape and beauty. Because massive objects cannot reach light speed, the region below that speed becomes a vast landscape of possibility. Time dilation grows without ever becoming total. Energy demands grow without ever yielding the final step. The closer you get to the boundary, the more extreme the effects become, which is precisely why relativity remains so rich for thought experiments and for the physics of particles and astrophysical objects. The barrier is not the end of interest. It is what defines the interesting terrain. Still, one should resist the temptation to soften the impossibility by saying things like, nearly light speed is basically the same thing. It is not. Near light speed can be enough to produce enormous time dilation, true, but nearly and exactly are separated by the most unforgiving kind of difference. A finite but huge effect is not the same as the boundary case. A traveller moving unimaginably fast may age far less than those at home. A traveller at light speed would not be a meaningful extension of that trend for a massive body, because the theory does not assign that body such a state in the first place. The boundary is not just a larger number, it is a categorical edge. There is something philosophically clarifying about that. Much of the dream of immortality depends on taking a trend and assuming it can be pushed to completion. If a little more life is good, perhaps endless life is just more of the same. If slowing time is possible, perhaps stopping time is just the limit case. Physics often teaches the opposite lesson. Trends can run into walls. Continuity of intuition can break at the boundary. The universe is full of behaviours that remain smooth right up until they reach a region where the underlying structure sees no further. That is what happens here. One might ask whether some future trick could bypass the need for a massive object itself to reach light speed. Could one warp space-time, or use shortcuts, or exploit still unknown principles? Such possibilities belong to different conversations and often to much more speculative physics. They are not what special relativity itself allows. Within the framework we are discussing, the rule stands. Massive objects can approach light speed indefinitely but cannot attain it. That's enough to frame the present question properly. If the hope is to live forever by moving fast enough, the answer cannot rely on actually getting to light speed, because massive beings do not get there. That realization does not ruin the wonder. In fact, it sharpens it. The story ceases to be about a naive sprint toward infinity and becomes instead a story about negotiation with limits. How much future can you reach without crossing the uncrossable boundary? How much can you slow your own aging while remaining a massive biological vulnerable creature? What does it mean that the universe allows vast temporal stretching but forbids total escape? These are more interesting questions than the simple fantasy of infinite speed, because they belong to real physics rather than wishful extrapolation. There is also a humane consolation in the limit, though it may not seem like one at first. A universe that permitted massive objects to reach light speed and thereby perhaps evade time altogether would be a universe very different from the one that supports stable matter, consistent causality, and the ordinary continuity of lived experience. The same rules that deny us that final step are also part of what makes the world coherent. We do not get immortality through velocity, but we do get a universe whose behaviour can be understood, tested, and trusted. That is not a small exchange. And so the answer to why nothing with mass can reach light speed is not a single mechanical obstacle, but a convergence of relativistic truth. The speed of light is not just another speed. It is a boundary built into space-time. Massless things inhabit it naturally. Massive things do not. As a massive traveller accelerates closer and closer to that boundary, the required energy rises without limit. The gains in speed become ever harder won, and the final step remains forever out of reach. You may chase the horizon, but the horizon does not become pavement beneath your feet. This means that the dream of using motion to escape aging has a ceiling, even if that ceiling lies fantastically high, above anything human civilization can presently touch. You can slow your time greatly. You can make your life reach farther into the future of the universe. You can, in principle, return younger than those who stayed behind. But you cannot outrun time completely by becoming light-like. Mass forbids it. The laws forbid it. The structure of the theory forbids it. Once that settles in, the next question becomes even more sobering. If actually reaching light speed is impossible, then even approaching it closely enough for dramatic time dilation would require extraordinary effort. Just how extraordinary? What would the cost be in energy, technology, and sheer physical demand? The romance of relativistic travel is one thing. The bill for it is another altogether. Once it becomes clear that nothing with mass can actually reach the speed of light, the next thought is usually a practical one. Fine. Perhaps we do not need the full thing. Perhaps close enough will do. If the dramatic slowing of time begins long before the final limit, then maybe the real goal is not light speed itself, but something near it. Near enough that years on board become small compared with years on Earth. Near enough that a human being could ride a ship into a distant future, while giving up only a modest slice of their own lifetime. Near enough to get the effect without demanding the impossible. And this is where the romance of the idea runs into its next serious obstacle. Because even if we lower the ambition from reaching light speed to merely approaching it, the cost does not become friendly. It remains crushing. That word is not chosen for drama. It is chosen because the problem is not a small engineering inconvenience that vanishes if one adds better materials, more efficient engines, and a committee willing to work through lunch. The closer you try to get to light speed, the more severe the demands become. The required energy rises to staggering levels. The ship becomes a machine not just for travel, but for handling an almost absurd amount of stored and directed power. The fuel problem becomes monstrous. The infrastructure behind the mission begins to look less like a project, and more like an entire civilization deciding that one human voyage is worth the effort of moving a mountain made of energy. It helps to start with something ordinary. Moving an object from one place to another always costs something. Push a chair across the floor and you spend effort. Drive a car across a country and you spend fuel. Launch a spacecraft into orbit and you spend a frankly impolite amount of fuel for what is, in cosmic terms, still a very local outing. Space travel already asks for more energy than daily life gives us much intuition for. Escaping Earth is expensive before one even begins talking about relativistic motion. The rockets we build today burn extraordinary amounts of fuel merely to lift payloads into orbit or send probes through the solar system at speeds that are impressive by human standards, but still tiny compared with the speed of light. That is the first scale correction worth making. When people imagine a ship going very fast, they often imagine a simple continuation of present-day spaceflight. Faster engines, larger tanks, stronger hull, perhaps a sleek design if one has been influenced by too many film posters. But the gap between our current speeds and the kind of speeds required for dramatic human time dilation is not the gap between a car and a sports car. It is not even the gap between a bicycle and a jet. It is so large that ordinary language about faster travel begins to lose its grip. To chase near light speed, you need not just a lot of energy, but a truly vast amount. And because a spacecraft has mass, every bit of fuel you carry to accelerate it also has to be accelerated. That fact turns space travel into a deeply annoying exercise in self-burdening logistics. You want fuel so you can speed up, but the fuel itself makes you heavier, which means you need more fuel to speed up the fuel, which means you become heavier still. The problem spirals. Rockets are like travelers who pack suitcases full of additional suitcases in case the first suitcases turn out not to be enough. This is already a challenge for ordinary missions. For relativistic missions, it becomes far worse. If you want a human ship to approach light speed, you need either a propulsion method far beyond the chemical rockets we know, or an energy source so dense and so efficient that it belongs closer to the imagination of advanced theoretical engineering than to anything currently sitting on a launch pad. Chemical fuel is nowhere near enough. It is admirable stuff for getting off a planet and terribly committed in its own loud combustible way. But on relativistic scales, it is hopeless. Even nuclear options, far more energetic than chemistry, become difficult once the target speed grows extreme. The farther toward light speed you aim, the more absurd the mission budget in energy becomes. And it is not only a matter of reaching the speed. If this were a journey a human being was meant to survive and perhaps return from, the ship would not simply need to accelerate once and be done. It would need to speed up, possibly coast, and then slow down again if arrival at the destination is meant to involve something gentler than hurtling through the target system like a very expensive and highly philosophical bullet. Then, if there is a return trip, the whole story repeats in reverse. Every gain must later be paid for again in braking. That doubles the challenge in a very unfriendly way. It is not enough to get fast, one must also stop being fast. Stopping in space is one of those details that sounds obvious after it's pointed out and somehow still manages to be forgotten whenever imagination gets excited. In daily life, we're used to friction doing much of the work. Cars stop because brakes and air and rolling resistance all join forces to oppose motion. Space is not so helpful. If you accelerate to a tremendous speed, you carry that tremendous speed with you until something changes it. A ship trying to visit another star system at relativistic velocity would need a serious plan not just for departure, but for arrival. Otherwise, the mission is less a visit and more a drive-by on the grandest scale possible. This means the propulsion challenge is not merely about power in the abstract. It's about controlled power over long periods, with enough efficiency to make a large human-rated spacecraft undergo enormous changes in velocity without demanding an impossible mass of fuel. One begins to see why the topic quickly migrates from exciting idea to civilization-scale commitment. A single relativistic human mission may require resources comparable to what whole nations currently consume for countless ordinary purposes. We're not talking about a wealthy person funding an ambitious ride. We're talking about a society deciding to dedicate a portion of its industrial soul to one act of temporal asymmetry. There is another hidden cost as well, and it has to do with time in a less romantic sense. If you want human travellers to survive acceleration comfortably, you cannot simply hurl them to near light speed instantly. Human bodies are not especially enthusiastic about sudden violent changes in motion. There are limits to what flesh, organs, blood circulation, and delicate inner structures can tolerate. So a realistic journey would likely involve prolonged acceleration over time, perhaps at a rate gentle enough that the crew remains functional and conscious and does not spend the mission becoming soup. But prolonged acceleration means prolonged energy expenditure. It means the ship is not just igniting once in a dramatic burst and then enjoying the future. It is working continuously, pouring energy into motion for extended spans. That creates an interesting emotional contrast. From the outside, the public might imagine a sudden leap into near-light speed. From the inside, the crew might experience a long engineering grind. Systems checks, heat management, constant monitoring, continuous thrust. Relativistic travel, if it ever becomes possible, may feel less like a miraculous jump and more like an extremely demanding ongoing process in which the ship spends a very long time earning every fraction of the desired speed. Heat itself becomes another problem. Whenever one handles enormous energy, one must deal with waste heat, inefficiency, and the general tendency of physical systems to become distressingly hot when pushed hard. On Earth, we can often dump waste heat into the air or water. In space, cooling is much less cooperative. A relativistic spacecraft would need not just engines of extraordinary power, but a way to prevent itself from cooking its own interior while operating them. That means radiators, thermal management, shielding, and a design philosophy built around the fact that powerful machines are rarely tidy. They sweat in the language of heat, and space gives them fewer ways to wipe their brow. Then there is shielding. Strictly speaking, the biological consequences of high-speed travel belong to the next part of our subject. But the engineering burden begins here. At extreme velocities, even sparse interstellar material becomes dangerous. A tiny grain of dust striking the front of a ship at relativistic speed is not a quaint inconvenience. It carries enormous destructive potential. The faster you go, the more serious that danger becomes. So the ship must not only accelerate itself to astonishing velocity, it must also survive a universe that becomes increasingly hostile the faster it moves through it. That implies robust forward shielding, advanced detection, perhaps active defenses, and all of that adds mass. More mass means more energy required. The problem loops back on itself again. This is the recurring theme of relativistic engineering. Every solution makes the ship heavier or more complex, and every increase in heaviness or complexity intensifies the original propulsion problem. Need more shielding, more mass, need more fuel, more mass, need larger structures to house the fuel and support the engines. More mass need better cooling. More mass need redundancy, so a single failure does not end the mission. More mass. It is almost comic in its persistence, except that the joke is on the budget, the mission planners, and anyone who hoped the ship might be sleek. This is why many serious discussions of interstellar travel eventually move away from crude ships and toward robotic probes, sails driven by external energy sources, or other concepts designed to avoid hauling large, fragile biological cargo through a relativistic regime. A machine can survive conditions a human cannot. It can tolerate long delays, narrow spaces, and certain kinds of risk more cheerfully, because it is not required to enjoy the experience. A human crewed relativistic mission asks for all the hard parts of high-speed travel, plus the extra burden of keeping a group of biological organisms alive, healthy, sane, and minimally mutinous inside a machine, moving at a pace the universe makes very expensive. Economics enters the story as well, and not just in the narrow sense of money. Money is only a way societies count priorities. The deeper issue is resource allocation. What would it mean for a civilization to build one or several ships capable of approaching light speed? How much infrastructure would be needed? How many power stations, mining operations, factories, research programs, and launch systems would have to exist in support? How much political continuity would be required to maintain such an undertaking across the years or decades needed to prepare it? Grand projects on Earth already struggle under the weight of changing governments, public impatience, shifting budgets, and the human tendency to become distracted by nearer concerns. A relativistic human mission would need extraordinary continuity of purpose. It would not be only a scientific project. It would be a test of whether a civilization can stay committed to one vast goal long enough to realize it. One can even imagine the public conversation around it. Some would see it as the boldest expression of human curiosity. Some would call it wasteful. Some would argue that the same energy and technology ought first to repair problems at home. Some would say that building a ship so one person can arrive in the future younger than the people left behind is either the noblest thing humanity ever did, or the most elaborate midlife crisis ever financed by a state. All of that would become part of the cost. The crushing burden is not only physical, it is social, political, and moral. And even if a civilization accepted that burden, another hard truth remains. The mission would almost certainly demand extraordinary precision. At near light speed, small navigational errors become serious. Tiny particles become threats. Engine failures become catastrophes with very little room for improvisation. A ship travelling at such velocity does not get many casual second chances. It is operating in a regime where mistakes carry the force of major disasters, so the engineering standard required would be severe. Redundancy, reliability, fault tolerance, autonomous repair, shield integrity, environmental systems, communication strategy, navigation across vast distances. Every one of these would need to function under conditions more extreme than anything current human spaceflight has faced. That is why the energy problem, though central, is not the whole story. Even if by some miracle the power source were handed to us tomorrow in a tasteful container with easy instructions, the ship would still need to survive the consequences of using that power. Speed is not only hard to gain, it is hard to inhabit. Near light speed is not merely a number on a display, it is an environment of difficulty created by your own motion. There is also a humbling contrast between theory and practice here. Special relativity says dramatic time dilation is possible in principle. That is already enough to change our understanding of what time is. But principle is one thing, and mission architecture is another. Physics can permit an effect without making it convenient. The universe says yes, motion can let you age less relative to the outside world. It does not say yes, and here is an affordable propulsion system, a shielding solution, a thermal plan, a launch schedule, and a nice informative brochure. The theory opens the door and then reveals that the staircase behind it is very steep. In some ways, that makes the subject more interesting, not less. If the cost were trivial, the idea would feel almost cheap. It would become a routine trick, a scheduling tool for ambitious people with long-term plans. Instead, the crushing expense preserves the grandeur of the effect. To move through time differently, you must pay in energy, engineering, and probably civilization scale coordination. The universe allows the distortion, but it asks a frightening amount in return. That seems almost fair. A trick this deep should not be easy, and yet one should be careful not to treat the cost as merely a reason to dismiss the whole idea. Human history is full of things once dismissed as impossibly expensive or impractical that later became ordinary. Flight, space travel, electronic computation, all would have sounded wildly ambitious before the right breakthroughs. The difference here is not that difficulty implies impossibility. The difference is that relativistic human travel demands such a concentration of physical resources that even optimistic futures must treat it as a major undertaking, not a consumer option. It is not tomorrow's airline. It is, at best, the project of a civilization that has learned to command extraordinary amounts of energy with great discipline. That thought leads naturally toward the next question. Suppose, for the sake of argument, that the energy problem is somehow managed. Suppose the engines work, the ship accelerates, the shielding holds, the navigation stays true, and a human crew is actually carried into the regime where time dilation becomes dramatic. There is still the small matter of the crew themselves. Flesh is not steel, bones are not bulkheads. Minds do not function like guidance systems. A ship may survive near light-speed travel on paper and still be a miserable or lethal place for the living beings inside it. Once the cost of chasing the speed is acknowledged, the next issue is the cost of enduring it. By this point, the idea has become very tempting in a very dangerous sort of way. Motion can slow your aging. A ship could, at least in principle, carry you into the future while sparing you from living through all the years that pass outside. The closer you push toward light speed, the more dramatic the effect becomes. That part feels almost intoxicating to think about. But there is a reason the subject cannot remain comfortably in the realm of abstract physics for long. The moment you place an actual human being inside the spacecraft, the question changes. It is no longer only about what relativity permits. It becomes about what a body can endure, what a machine can protect, and what survival really means when the journey itself becomes extreme. That shift matters because there is a tendency, especially when people imagine great scientific possibilities, to treat the human body as an afterthought. We imagine the ship first. We imagine the destination. We imagine the strange beauty of arriving in a future century while still young by comparison with the world we left behind. Only later do we remember that a person is not a neat abstract point gliding through an equation. A person is soft tissue, circulating blood, vulnerable nerves, bones that need loading, muscles that weaken when they are not used properly, and a brain that can be remarkably clever about physics while still becoming tired, lonely, confused, or frightened in a sealed metal structure very far from home. So even if we set aside for a moment the crushing energy cost of approaching relativistic speeds, we still run into another barrier. A ship may be able to move fast in theory. That does not mean the crew can remain alive and healthy during the process. The first issue is acceleration. People often imagine high-speed travel as if speed were a state you simply switch on, the way a light comes on in a room. But speed has to be built. If you want a ship to go very fast, it has to accelerate, and if you want the people inside it to survive in good condition, that acceleration has to be managed carefully. Human beings can tolerate only so much force before organs, blood flow, and consciousness begin to fail in unpleasant ways. We are not designed to be hurled about like luggage, though even luggage generally objects if treated badly enough. A gentle acceleration sustained over a long time might be one way to handle this. In fact, in some imagined interstellar journeys, a prolonged, comfortable acceleration is often treated almost as a luxury, because it gives the crew something close to artificial gravity inside the ship. That sounds appealing. You walk, exercise, and live under a steady pull rather than floating. But comfort comes with a cost. If you accelerate gently, you need to do it for a long period to build up the required speed. That means long engine operation, long exposure to the stresses of propulsion, long periods in which every system aboard the ship must continue performing well. A brutal acceleration might harm the crew quickly. A gentle acceleration might save them physically while demanding far more from the engineering. Survival does not become simple, it just changes shape. Then there is the basic fact that the human body does not enjoy long isolation in artificial environments, even before relativistic concerns enter the picture. We already know from ordinary spaceflight that extended time away from Earth places strain on nearly every system of the body. Muscles weaken if they are not loaded properly. Bone density can fall. Fluids shift in strange ways. Sleep can become irregular. Stress accumulates. Small problems can become serious when there is no easy rescue, and no nearby hospital filled with people whose job is to look alarmed in useful ways. Now imagine all of that inside a ship designed not for a short orbital stay, but for a long, deeply isolated relativistic mission. The body would not merely need to survive a stunt, it would need to endure an entire alternate way of life. This means the ship itself must become something more than transport. It has to function as an ecosystem, a clinic, a shelter, a training space, a food system, a waste processing system, a psychological habitat, and a protective shell against an environment that grows increasingly hostile the faster you move through it. The romance of star travel often focuses on the view through the window. The reality would focus more on air quality, water recycling, maintenance, repair, microbial control, exercise routines, medical contingency plans, and whether the life support system continues behaving itself under demanding conditions. If the ship fails in some ordinary way, relativity will not step in to comfort the crew. Slowed time does not help if the oxygen system breaks. Radiation becomes one of the most serious dangers. Space is already a place where radiation exposure matters. Outside the natural shielding of Earth, people face energetic particles from the sun and from deeper space, and those exposures are not merely technical footnotes. They can damage tissue, raise cancer risk, and threaten long-term health. At relativistic speeds, the problem changes again, because the ship is no longer just sitting in a dangerous environment. It is ploughing through it at extraordinary speed. Particles and dust that might be relatively harmless at low speeds can become far more threatening when encountered head-on, at extreme velocity. A tiny bit of matter striking the ship at those speeds can carry devastating energy. So the crew needs shielding, serious shielding, not symbolic shielding, not decorative shielding, not the kind of shielding one adds because it looks reassuring in a design sketch. Real shielding, dense enough and well designed enough to protect living tissue from both ordinary radiation exposure and the intensified hazard of moving rapidly through sparse interstellar material. But shielding adds mass, and added mass makes the propulsion challenge harder. The moment you protect the body better, you burden the ship more. Every biological need pulls against every engineering limit. That is one of the most relentless themes of the entire problem. There is also the matter of collision risk. Space is often described as empty, and by everyday standards it is. But empty does not mean nothing. A relativistic ship does not need to strike a large object to have a very bad day. At sufficiently high speed, even a tiny particle can become dangerous. A grain of dust ceases to be a piece of grit and begins to resemble a weapon. The faster the ship moves, the more the universe in front of it behaves like a shooting gallery, made of things far too small to see in time with ordinary human reflexes. That means the ship needs not only shielding but detection, perhaps deflection, perhaps layered defences, and certainly a design that assumes impacts may happen. Now add the human factor. Imagine living inside a vessel that must trust its forward shielding every hour of every day, knowing that the vastness ahead is not perfectly empty, and that your own speed turns microscopic material into existential threat. It is one thing to admire the idea from a lecture or a quiet evening under a blanket. It is another thing to sleep inside the machine and know exactly what its failure would mean. Survival is physical, but it is also mental. A crew would need not only robust bodies, but trained minds, resilient enough to live under prolonged dependence on systems that cannot be allowed to fail. And failure is never just one thing. On a long voyage, systems wear down. Components age, materials fatigue. Tiny faults become larger ones if not detected early. Software behaves in ways that seemed impossible right up until it did them anyway. Seals degrade, filters clog, pumps fail, sensors lie. Any machine that must keep humans alive over long periods must be prepared for the fact that reality is full of boring problems that do not care how historic the mission is. The ship might be one of the greatest engineering achievements in history and still be defeated by some persistent small issue that began as a minor irregularity on a monitor. Human survival in space has always depended as much on mundane reliability as on grand design, and a relativistic craft would raise that requirement to an extreme. Then there is medicine. On Earth, a medical emergency occurs within a civilization. There are hospitals, specialists, supplies, second opinions, blood banks, surgical teams, and the possibility of making someone else responsible for the decision while you sit in a corridor trying not to imagine things. On a relativistic ship, the crew carries its medicine with it. If someone falls ill, is injured, develops an infection, suffers a mental health crisis, or experiences a condition no one predicted, the ship must respond from within itself. That means medical training, medical equipment, diagnostic capability, pharmaceuticals, surgical possibility perhaps, and procedures for cases where the best available option still may not be good enough. Aging itself becomes a strange topic in this setting. Relativity may slow your aging relative to people back on Earth, but it does not make you biologically invulnerable during the years you do live. If your journey takes 10 subjective years, you still live 10 subjective years as a body subject to disease, wear, and accident. You're not wrapped in a protective myth just because history outside is moving faster. From your own point of view, you still need sleep, nutrition, exercise, stress management, and protection from all the ordinary things that can go wrong in living tissue. Time dilation helps you spend fewer years relative to others, not fewer years relative to yourself. That distinction becomes even sharper when one considers psychological endurance. A long journey in a closed environment is not simply a physical trial, it is a mental one. Human beings are social animals with complicated emotional rhythms. We are influenced by light cycles, novelty, privacy, shared rituals, meaningful work, and contact with the larger world. Remove enough of that and the mind begins to behave strangely. Confinement can sharpen conflict. Isolation can distort perspective. Monotony can flatten motivation. Anxiety can become self-reinforcing. Small irritations can grow teeth. Even a highly trained crew could face emotional strain that no amount of physics brilliance would cancel. Communication delays only deepen the problem. The farther the mission ranges and the faster the ship moves through its route, the less immediate Earth can feel. Advice cannot always arrive in time. Comfort cannot arrive in time. Even conversation may lose its normal rhythm. A crew might send a message and receive the response only after the emotional moment that prompted it has long since passed. Over enough distance, Earth becomes not a living companion but a delayed archive. That changes how loneliness works. You're not merely far away. You're temporarily estranged from the very society that launched you. And this is where survival becomes more than staying alive in the narrow sense. A person can remain breathing and still be worn down by dislocation. To survive a relativistic mission in a meaningful human sense, the crew would need purpose, structure, healthy relationships, routines, recreation, variation, and a design of shipboard life that respects the mind as much as the body. It is not enough to protect organs from damage if despair or conflict make the environment corrosive. A well-designed future ship would need to be psychologically intelligent. It would need spaces for privacy and companionship, work that matters, rhythms that prevent time from becoming featureless, and perhaps some way of preserving the emotional reality of connection to a world that is aging away from you more quickly than you are aging yourself. There is another complication hiding inside the dream of reaching the future while staying young. Suppose the crew succeeds. Suppose they remain healthy, the ship holds together, and they arrive in a much later era than the one they left. What then? Survival is not complete at arrival. The destination itself may be hard on the body. Gravity may differ. Atmospheres may be unsuitable. Technologies may be unfamiliar. Medical standards may be better, but cultural standards may be baffling. Even returning to Earth may present biological and psychological challenges if the Earth you return to no longer resembles the one your body was prepared to inhabit. Survival includes re-entry into meaning, not just continuation of heartbeat. One can also imagine cumulative effects. A person who repeatedly undertook relativistic journeys might preserve more of their youth relative to history, yes, but repeated deep missions could also accumulate hidden burdens. Radiation dosage might build, psychological strain might deepen, musculoskeletal problems might recur, social dislocation might become profound. The body might be younger than the century around it, yet still marked by the specific hardships of ship life. In that sense, the preserved traveller may not resemble the fantasy of agelessness at all. They may be relatively young in years, but heavily shaped by the price of staying that way. This is perhaps the key correction to the romantic image. We picture the near light-speed traveller as somehow drifting above ordinary frailty, because relativity has given them an unusual relation to time. But the opposite may be closer to the truth. To achieve that unusual relation, the traveller must pass through some of the most demanding physical and environmental conditions imaginable. Their youth relative to Earth may be brought through an existence that is in many ways harsher than ordinary aging at home. The ship protects them, but only by becoming an immensely complicated artificial world whose every success depends on relentless maintenance and good fortune. And of course, the ship itself is not immortal either. Materials degrade, shielding erodes, systems age, microscopic impacts accumulate, repairs consume supplies. Even in an ideal mission, the spacecraft is not a magical object standing outside entropy. It is a machine fighting entropy every day. That gives the whole enterprise a subtle irony. Time dilation may let the crew spend fewer years while the outside universe spends more. But inside the ship, both life and machinery are still engaged in the same old battle against decay. The future is not reached by escaping wear. It is reached by surviving it in a carefully managed form. This is why biological constraints matter so much to the original question about living forever by moving fast enough. Even if physics grants you the ability to slow your aging relative to the rest of the universe, you remain a biological creature with needs, vulnerabilities, thresholds, and breaking points. You do not become a pure clock. You remain flesh under engineering. Relativity changes the timing of your mortal journey. It does not remove mortality's texture. There is something honest about that. The body prevents us from turning an extraordinary physical insight into a childish fantasy of easy eternity. Your ship may be elegant. Your mission may be historic. Your relation to time may be radically altered. But you still need air, water, food, sleep, warmth, medicine, companionship, and protection from a universe that becomes more dangerous the faster you challenge it. In the end, survival is never guaranteed by velocity. It is negotiated through design, discipline, and luck. So when we ask whether moving fast enough could let you live forever, we're really asking two questions at once. One belongs to relativity and asks how motion changes aging. The other belongs to biology and asks whether a human being can endure the means by which that motion is achieved. Physics answers the first with a qualified yes. Biology and engineering answer the second with a long list of warnings. Yes, time can be stretched relative to the outside world. Yes, a traveller could in principle reach farther into the future than a stationary life would allow. but the body must still survive the journey, and survival at those extremes is not a trivial detail to be solved later. It is part of the central truth. Once that becomes clear, the final issue begins to come into focus. Even if the ship works, even if the crew survives, even if relativity gives you a way to carry your finite years farther across the timeline of the universe, does that actually amount to immortality? Or is it something different, something remarkable but more limited, a way not of defeating time but of changing the terms on which you meet it? And so we arrive at the part of the question that sounds the simplest and turns out to be the most important. If motion can slow your aging, if a fast enough ship can carry you into a distant future while only a smaller amount of time passes for you, if you can return younger than the people who stayed behind, then what exactly have you gained? Is that immortality? Is it some scientific version of living forever? Or is it something stranger, more limited, and in a way more revealing about what we really mean when we talk about wanting more time? By now, the shape of the answer is beginning to emerge. Relativity does allow something extraordinary. A person can, in principle, extend their experienced lifetime relative to the rest of the universe. That is not a poetic way of putting it. It is a physical fact. Move fast enough for long enough, and your own clock, along with your body, your biology, your aging, and your private sequence of lived moments, will accumulate less time than the world you left behind. You can cross a great distance into the future while spending far fewer years of your own life than everyone else spends waiting for you to arrive. That is astonishing. It would have sounded absurd for most of human history. We are used to thinking that the future can only be reached at one speed, the ordinary speed of living through it. 1 year of your life buys 1 year of history, more or less, and that is that. Special relativity breaks that expectation. It says no, there is another arrangement. Your personal years and the years of the outside world do not have to stay in lockstep. A finite life can be made to reach much farther into the future than common sense once believed possible. And yet, despite all that, the word immortality still overshoots the truth. Immortality means more than historical reach. It means not ending. It means remaining in existence without running out of your own time. It means that however long the world continues, you continue too. Relativistic travel does not offer that. It offers something more selective. You still live through your own days one by one. You still age according to your own clock. Your heart still beats. Your cells still change. Your body still accumulates wear according to the time you personally experience. However dramatic the time dilation becomes, you do not step outside your own lifespan. You still have one. This is the central distinction, and it matters so much that it is worth circling carefully. If you take a journey at enormous speed and only 5 years pass for you while 50 years pass on Earth, then from the point of view of the Earth, you have gained something remarkable. You have advanced 50 years into the future while paying only 5 years from your own life. But from your own point of view, you have still spent 5 years. You did not skip the cost entirely. You only changed the exchange rate between your private time and the world outside. That means you can outlast time in one sense, but not in another. You can outlast ordinary historical pacing. You can outlast the assumption that a single lifetime must remain tied to a single familiar era. You can become a person whose finite years stretch unusually far across the timeline of civilization. But you cannot outlast mortality itself just by moving fast. Mortality remains attached to your own experience duration, and that duration, though it can be slowed relative to others, continues moving forward. There is something almost comforting in that, even if it disappoints the more ambitious fantasy. The universe allows a profound rearrangement of time without allowing a complete escape from it. It gives us reach, but not endlessness. It gives us a way to carry a limited life farther into history, but not a way to make that life infinite. Seen another way, relativistic travel does not defeat death. It defeats synchrony. That may sound like a small change in wording, but it captures the entire truth of the matter. What the fast traveller really escapes is not their own finitude, but the ordinary agreement between their aging and everyone else's aging. They no longer move through history at the same pace as the people who stayed behind. They break ranks with the shared rhythm of life. Their body remains mortal, but their mortality becomes detached from the calendar of the wider world. That is why the idea feels so close to immortality without ever becoming it. A being who lives through many eras can look almost immortal from the outside, even if from the inside they are still using up a perfectly ordinary, limited store of personal time. This is perhaps why the idea touches something so deep in the human imagination. Most people do not only want endless subjective duration, they also want continuity with the future. They want to know what comes next. They want to see whether humanity gets wiser, kinder, healthier, stranger, more capable, or merely more efficient at creating problems that require urgent software updates. They want to witness outcomes they will otherwise never see. Relativity gives a narrow but real answer to that desire. It says that the future is not sealed behind an absolute wall. Under the right physical conditions, you may enter it faster than ordinary earthbound living would allow. That is not a trivial consolation. For some people, it may be the more meaningful one. Suppose you care less about living forever from the inside and more about seeing farther. Suppose your deepest wish is not to gather endless years in the familiar present, but to witness what humanity becomes. In that case, time dilation begins to look almost generous. It cannot make you deathless, but it can make your limited life historically longer. It can let your years cast a farther shadow. But that gift, if we call it that, comes with a particular cost. We have touched on it before, and it belongs here as much as anywhere, because it reveals what outlasting time really means in human terms. To outlast ordinary historical pacing is often to lose ordinary companionship. You do not carry the people you love into the future just by preserving more of your own youth. If they do not travel with you, they remain bound to Earth's time. They age, they die, they pass through the decades you're effectively skipping. So the price of reaching farther into the future may be surrendering shared life in the present. That is why the dream never quite becomes a triumph. It remains mixed. A relativistic traveller does not simply gain time, they also lose alignment. They preserve some things at the expense of others. They may keep more of their body's youth, but they do not keep the ordinary flow of years with their family, friends, or culture. A person who rides into the future while aging slowly may arrive with a younger face and an older grief. And yet, there is something quietly noble in that too. It reminds us that time is not only a physical quantity, it is also a social one. Much of what makes a life feel full is not merely how long it lasts, but who it lasts with and in what kind of shared sequence. A normal human lifetime is not just a private clock winding down. It is a participation in the time of others. Childhood overlaps with someone else's adulthood. Friendships mature, families grow, communities remember together. Relativity can change your private rate of aging, but it cannot guarantee that shared overlap. If anything, it exposes how precious that overlap was all along. This may lead us to a deeper answer about immortality itself. Perhaps what people most often fear is not simply their own ending, but the ending of participation. The loss of being present in the world, present with others, present in the unfolding of events that matter to them. Relativistic travel partially answers that fear by offering continued presence across longer stretches of historical time. You may remain present in a broad external sense far longer than an ordinary stationary person, but it only partially answers it, because presence across history is not the same as presence within a continuous life shared with others. That is why the phrase living forever begins to feel less useful the longer one thinks about it. It hides too many different hopes under one dramatic umbrella. Some people mean endless subjective life. Some mean endless historical witness. Some mean freedom from aging. Some mean freedom from loss. Some mean simply more time to learn, love, rest, repair, and become less foolish. Relativity only addresses a narrow portion of that list. It does not free you from subjective finitude. It does not free you from the vulnerability of the body. It does not free you from separation. It only changes how your lived years line up against the years of the rest of the universe. And even that remarkable possibility remains tangled in all the practical barriers we have discussed. Near-light speed travel demands extraordinary energy. It demands technologies we do not yet possess at a level suitable for human voyages. It demands shielding, life support, medical resilience, psychological endurance, and a ship capable of surviving an environment made harsher by its own speed. In principle, yes, a person can extend their experienced lifetime relative to the rest of the universe. In practice, doing so may require so much from a civilization that the dream remains far ahead of our current abilities. Physics opens the door, but engineering, biology, and history stand in the corridor asking difficult questions. Still, it would be a mistake to dismiss the idea simply because it is difficult. Some truths matter even when they are unlikely to become everyday tools. The fact that motion changes time is one of those truths. It alters not just our technology, but our understanding of existence. It tells us that duration is not one universal stream carrying everyone equally. It tells us that the shape of a life depends partly on its path through space-time. It tells us that age is not only biology plus calendar, but biology plus journey. That is already a profound change in how we see ourselves. In a sense, this is the true meaning of outlasting time. It is not about becoming infinite. It is about discovering that time itself is not as simple, uniform, or impartial as we once assumed. A human life can be arranged differently against the structure of the universe. It can be stretched historically without being stretched subjectively. It can be made to intersect futures that would otherwise lie beyond it. That is not immortality, but it is far from ordinary mortality too. It is something in between, something physically real and philosophically unsettling. Perhaps the strangest part is that this conclusion makes time feel both more flexible and more serious at once. More flexible, because motion can alter its passage in ways that defy common sense. More serious, because even with all that flexibility, our own experienced time remains limited. You can slow the spending, but you cannot avoid spending altogether. You can carry your life farther into the universe's future, but you cannot make your personal stock of lived moments bottomless. Relativity teaches both possibility and restraint. It says yes, but not endlessly. It says more, but not forever. There is a quiet maturity in that answer. So much of science is not about granting the oldest dreams exactly as imagined, but about replacing them with something stranger and more precise. Alchemy did not give way to magical gold-making, but to chemistry. The dream of flight did not produce birds made of metal by sheer imitation, but aerodynamics, engines, and controlled lift. In the same way, the dream of outlasting time does not lead to simple immortality through speed. It leads to relativistic time dilation, to the possibility of asymmetric aging, to future travel without backward travel, to finite lives that can cross extraordinary spans of history. The childish version of the wish is denied. The deeper version is transformed. And maybe that transformed version tells us something useful about the present as well. Because even for those of us not boarding relativistic spacecraft anytime soon, the lesson is still quietly powerful. The value of time is not only in how much of it there is, but in how it is lived, with whom it is shared, and what kind of future it is aimed toward. The fast traveller can preserve more of their youth relative to the outside world, but they cannot preserve everything that makes time meaningful. That remains a useful warning against fantasies of quantity without relationship. More future is not automatically more life in the human sense. The content still matters. The overlap still matters. The ordinary days still matter. So can you live forever by moving fast enough? No, not in the literal sense. You cannot use speed to become truly immortal. You cannot reach light speed if you have mass. You cannot stop your own clock completely. You cannot turn a finite biological life into an endless one just by racing through space. But can you, in principle, extend your experienced lifetime relative to the rest of the universe? Yes. Absolutely yes. You can make fewer of your own years correspond to many more years outside. You can travel into the future in a physically meaningful way. You can outlast ordinary expectations about how far one lifetime reaches across history. That may not be forever, but it is still one of the strangest privileges physics permits. A person may remain finite and still become temporally unusual. They may never conquer time, yet still refuse to keep step with it. They may never be immortal, yet still arrive in ages that once seemed unreachable. And perhaps that is enough to leave us with a slightly different kind of wonder than the one we began with. Because in the end, the most remarkable thing is not that the universe gives us a loophole to eternity. It is that the universe is built in such a way that time itself is not the rigid background we once thought it was. It bends to motion. It separates travelers from those who stay. It allows a human being to spend 10 years and emerge into a world that spent far more. It refuses to grant forever, but it does permit a person, under the right conditions, to touch a much larger future than their own private years would seem to allow. And there is something fitting in that. We are creatures who will probably always want more time, whether for ourselves, for the people we love, or for the unfinished business of curiosity. Physics does not solve that longing. It does not tell us that endings are gone, but it does show us that time is richer, stranger, and less uniform than the old clock on the wall ever suggested. And maybe that alone is enough to soften the question a little. Not because forever becomes easy, but because the universe turns out to be far more interesting than a simple yes or no. So wherever you are listening from tonight, and whatever time it happens to be in your part of the world, perhaps the nicest thing to take from all this is not the fantasy of escaping time completely, but the quieter knowledge that time has more shape to it than we ever guessed. It can stretch, it can separate, it can play very different roles for different travellers, and while none of that makes us immortal, it does make every ordinary minute feel just a little stranger, and perhaps a little more worth noticing before it slips by.